tide movement and wave propagation. So this model as a whole requires just one large source at the bay to reproduce the arrival time, which in this case is about 5 minutes, as well as the large wave observed at the Pantaloan tide gauge record. Now, the second part to this story, and also the second proposed tsunami source mechanism, is fault displacement. So here we can see a schematic model of the west and the east block in the Palu Koro fault based on a hypocenter relocation. And this interestingly shows that the fault plane interface is deeper to the north into Dongala and actually follows the Macuster Strait bathymetry. And this is also consistent with other focal mechanism studies, which show a strike slip mechanism with a sharp dip angle of about 57 degrees. Okay. Now, if we consider this factor or mechanism alone, then we have to think that there has to be a significant component of dip-slip motion within the fault structure hidden beneath the bay to produce the vertical uplift necessary to generate the tsunami. But the analysis from the Pantaloan tide gauge record, as well as other tsunamis, have proven that the fault displacement alone was insufficient to generate a large tsunami. So this means that there is a bigger main cause at play, which in this case would be the proposed coastal and subaerial landslides. Okay, so here we can see how the literature has actually evolved around understanding the origin of the Palu tsunami. So the studies in black were field surveys that were conducted. So there were direct measurements taken in the field of, for example, inundation, run-up heights, etc. And in the red, we can see studies that have computed a tsunami model, which vary greatly in complexity. But for this particular talk, we are just going to focus on one comprehensive model published earlier this year, which is Sepulveda et al. Now, when we consider these many different tsunami models, there are two general concepts that are often relied upon, which we need to understand. So these are optical imagery and finite fault models. Okay, so the concept of optical imagery is that satellites have optical sensors which are used to generate images of the Earth over large areas and distinguish changes in landscapes. So these sensors function in the optical part of the wavelength spectrum, and this includes visible, near-infrared, and shortwave infrared wavelengths. And we can see a simplified diagram of this here. The second concept to understand when doing tsunami modeling is finite fault models. So a finite fault model is a modeled representation of the spatial extent, the amplitude, and the duration of the fault rupture or the slip of an earthquake. And this is generated via the inversion of teleseismic body waveforms and long period surface waves. Okay, so let's take a closer look at the Sepulveda et al. 2020 model published earlier this year. So figure A shows the regional map with major plate boundary faults of the Sula block. And we can also see historical earthquakes associated with tsunamis in the last century, which are indicated by a star and the name, and the year. So if we zoom in closer to Palu Bay, we can actually see the locations of the main Palu-Karo fault and the 4 fault geometries and their corresponding fault traces that have been proposed. So model 1, which is this magenta or this sort of purpley color, this has a straight fault trace beneath the bay, which actually is connecting the fault trace observed at Palu City to a point close to Pantaloan, which is here, and where the tide gauge record is that I mentioned earlier. Model 2, which is the orange here, assumes the same geometry on land as Model 1, but this follows the Palu-Karo fault along the coast and then makes a restraining bend in the middle of the bay. And then it goes back onshore to the north. Now, Model 3, which is the red, and Model 4, which is the green, these are both constructed with fault discontinuities beneath the bay. So these would also generate compressional vertical deformation for a left lateral strike slip mechanism. But Model 3 follows the main geologic trace of the Palu-Karo fault, and then it jumps to the observed northeastern fault trace here. And finally, Model 4, which, as I said, is in green, assumes a fault approximately aligned with the trough in the bathymetry along the central axes of the bay. So there are 3 main types of data used in Sepulveda's model, and these are INSAR, which stands for Interferometric Synthetic Aperture Radar, and this is an effective way to measure changes in land surface altitude. In addition, we have tide gauge records, which actually there are 2 for the Palu event, but mainly the Pantaloan record is identified as sort of most useful for many reasons. And finally, we have video-derived time histories, which have actually come from various social media sources. So with this data, a total of 12 static slip models of the 2018 Sulawesi earthquake have been created, and 4 different assumed fault trace geometries, which we discussed earlier, have been proposed with this. So the dip angles associated with each fault trace model vary from 70 degrees, and then 80 degrees, and then finally 89 degrees. And the color indicates the total slip magnitude, and the arrows here indicate the rake or the pitch. And as you can see, we have the RMS, the root mean square errors of each of the inversions shown here. So in this case, the geometry for model 1 is with a straight line fault trace beneath the bay, which shows a high slip just south of Palu Bay, and is also similar to what we have seen in other models proposed by Socket et al., as well as the USGS model. So model 2 is slightly different, and this is associated with a strong dip slip component of about 3 meters at the hypothetical bend, at the hypothetical fault bend, and this gives a larger tsunamigenic potential. And among all of these models analyzed, model 2, with the 70-degree dip in particular, is associated with the largest co-seismic contribution to the tsunami generation. Model 3 has one segment following the main Palu-Koro fault along the west side of the bay, which was also found in a previous study by Wilkinson and Hall in 2017. And since there are no direct signs of a fault trace in the bay bathymetry, this geometry would appear to be equally likely as Model 2. And yet again, you can see rather high slip here, not as much as the previous model, but still further to the south of the bay. And for Model 4, there are actually no specific observations to support this other than the large-scale bathymetry. And this has simply been included in the model in order to represent an intermediate value of the fault plane strike, which, as I mentioned previously, is through the central axes of the bay. Now, all of the inverted slip models show large slips at the southern end of the bay or south of the bay. And the high slip south of Palu City is well constrained by the significant co-seismic INSAR displacements. But also it's important to mention here that the results of the RMS errors are actually very similar for all of the models. So this makes it quite difficult to actually judge which model is best based on the fit to the INSAR observations. So this study also simulated run-up tsunami heights from the Palu tsunami. But first we must know what field observations are used, so then we can compare the simulated results with the field studies. And in this case, these are the data or field studies used. And in all of these studies, the maximum tsunami run-up found was about 10 meters, which is slightly above the, slightly more than other studies have found. So these are the results from the simulated tsunami run-up heights. Now, overall, none of the simulated tsunami run-up heights from the 12 fault models can fully explain the observed values, which, as we saw, exceed 10 meters in some locations, which was around southeast here. Now, model 2, with a dip-slip component of 70 degrees, has the largest vertical component of slip. And this produces run-ups comparable to those observed on the west coast, just north of minus 0.75 degrees, so about here. However, the simulations are all well below the observed run-up values for the rest of the bay. Here we can see 15 landslide source locations, which have been identified from existing studies and were used for the tsunami inversion. And the colored map in the middle represents the simulated maximum tsunami surface elevation in the 30 minutes following the earthquake. And on the right and left-hand panels, these are images from the video footage from social media, which show the initiation of tsunami waves along the bay, apparently due to submarine landslides. And as you can see, there have been 15 sourced. So we can actually see here that the largest landslide sources are actually found between latitudes approximately minus 0.86 to approximately just above 0.75, minus 0.75 degrees. So this is pretty interesting because this suggests that the landslide generated tsunami run-up has a similar north-south variation along the coast to that of the earthquake source, because strong motion strong ground motion focused near the location of the maximum slip was strong enough to generate larger landslides. Now, a sensitivity analysis of the inversion results to the observed locations was also completed. So the right and the left panels show a comparison of the simulated run-up heights with time histories at assumed locations about 200 meters further from the coast, as well as the original locations, which are the black dots. And the hypothetical ones are the green dots. And in the middle panel, we can actually see the maximum water elevation associated with this new inversion. So there's actually one big point to take from this slide. So that is that the simulated run-up heights on the western coast have smaller differences compared to the eastern coast, which have much larger differences. And what this model proposes is that this is due to greater contributions from a secondary tsunami source, which in this case is a small number of dominant landslide sources, which you can see here in the warmer colors. So. Okay, so when we consider the whole study of Sepulveda, one main conclusion can be found, and that is that coast-seismic deformation played only a minor role in generating the Palu tsunamis. And several landslides in Palu Bay were the major contributors to the tsunamis. Now, if we look back once more at the evolution of the tsunami literature, we can actually see a commonality that has come up frequently in most of the models. And this is that the run-up simulations seem to consistently underpredict observed run-up values. So this raises a bigger question of what is still missing from the tsunami models, if anything. Well, if we take a look at or think about what the absolute ideal tsunami model is, the literature actually shows an interesting pattern. So most of the models, they use field measurements, which now more and more are becoming available. But we also know that there are 2 tide gauge records available for this particular event. And these have proved somewhat useful for most models. But where the complexity seems to be is in recreating and simulating accurate tsunami arrival times for all 2 or 3 proposed tsunami waves. So maybe sometimes they get the first wave correct, but then they can't get accurate results for the second and third wave. So once we consider all of these 3 components here, this then needs to be integrated with an accurate earthquake rupture model. Now, yes, so we know that many rupture models have already been published, but the difficulty lies in accurately constraining the fault geometry beneath the bay in particular. And what appears to be missing from the literature are new high-resolution bathymetric and subsurface geological surveys covering the entire bay in order to determine whether there is any evidence of fault-related seafloor deformation patterns beneath the bay. So all of these components in some ways can be done individually, but what actually makes the most complete comprehensive model is how well all of these components actually unify. And this seems to be one of the biggest challenges at the moment with tsunami models. So to summarize, there are a few important things to learn from the Palu tsunami. So we know that this is a unique event, and in many ways, it actually questions conventional ideas of tsunami hazards related to strike-slip earthquakes. Furthermore, tsunami models need to be validated by accurate and available tide gauge and field survey data, which can then be integrated with an accurate rupture model. And lastly, very importantly, unique tsunamis such as in Palu are difficult to provide warning for, and that tsunami hazard assessments in strike-slip environments should include triggered landslides, especially for locations where the coastline morphology is strongly linked to the fault geometry. So thank you all very much for your time, and I hope you enjoyed this talk, and I'm happy to take any questions.
Thank you, Marcella.
Thank you, Miss Marcella. Great presentation. I will give the summary about the topic in bahasa. Is it okay?
Yes, no problem.
Oke. Selamat pagi Bapak Ibu. Baru saja Miss Marcella mempresentasikan mengenai the origin of the 2000 Palu tsunami, di mana catatan saya adalah presentasinya, poin-poinnya antara lain Miss Marcella di awal menjelaskan mengenai regional tektonik Palu, di mana Sulawesi berada di antara 8 zona konvergensi dan 3 lempeng utama, di mana pertemuan 3 lempeng ini membentuk pola pertemuan lempeng yang sangat kompleks. Dan untuk kota Palu sendiri berada di jalur sesar Palu Koro yang memanjang dari arah selatan tenggara Palu hingga ke utara Teluk Palu. Dan sesar ini sendiri tergolong sebagai salah satu sesar aktif di Indonesia. Kemudian kedua tadi, Miss Marcella menjelaskan mengenai historis tsunamigenic earthquakes selama 10 tahun terakhir di bagian timur Indonesia khususnya, di mana tercatat di tahun 2008 terjadi gempa besar dengan magnitud 7,4 di Sulawesi Utara dengan dirilisnya warning tsunami akibat gempa tersebut. Kemudian yang ketiga tadi juga dijelaskan historis kejadian gempa bumi selama 10 tahun terakhir, di mana gempa bumi Palu 28 September 2018 dengan magnitud 7,5 tercatat menjadi salah satu gempa besar yang pernah terjadi di Sulawesi. Dan gempa bumi dan tsunami yang terjadi di Palu merupakan fenomena yang unik dan menjadi perhatian. Mengapa? Karena epicenter gempa yang berada di segmen sesar Palu Koro ini memiliki mekanisme sumber sesar geser sinistral. Sedangkan gempa bumi yang menimbulkan tsunami umumnya terjadi di sekitar zona subduksi dengan mekanisme sesar naik atau turun. Yang menjadi pertanyaan besar adalah apakah tsunami Palu murni disebabkan oleh deformasi seismik atau faktor longsoran yang terjadi akibat dari guncangan gempa bumi tersebut. Nah, ini beberapa penelitian dan studi sudah dilakukan untuk mengidentifikasi sumber penyebab terjadinya tsunami Palu. Dari kesimpulan penelitian tersebut, yaitu faktor yang kompleks antara kedua-duanya. Kemudian tadi Miss Marcella juga menjelaskan mengenai perkembangan penelitian mengenai tsunami Palu, di mana ada 2 metode yang digunakan dalam penelitian mengenai tsunami Palu, yaitu yang pertama dengan menggunakan modeling tsunami dan dengan menggunakan data hasil survei lapangan. Miss Marcella membahas mengenai penelitian modeling tsunami dari Sepulveda et al., di mana pemodelan tsunaminya menggunakan 2 konsep utama, yaitu optical imagery berdasarkan data satelit dan finite fault model. Dan berdasarkan hasil pemodelan dari Sepulveda menggunakan 4 geometri sesar yang berbeda di sepanjang Teluk Palu, penelitian Sepulveda ini menggunakan 3 data, data satelit INSAR, data rekaman pasang surut, dan data waktu tiba gelombang tsunami dari berbagai sumber. Dibuat 4 model distribusi slip sesuai dengan geometri sesar yang sudah ditentukan di awal. Kemudian mereka juga menggunakan data run-up tsunami yang dirujuk dari beberapa penelitian dengan ketinggian tsunami maksimum mencapai 10 meter dan dikomparasikan dengan modeling yang telah ditentukan sebelumnya. Kesimpulan dari penelitian Sepulveda ini adalah deformasi koseismik hanya memiliki peran sedikit dalam membangkitkan tsunami di Palu. Dan sebaliknya, kontribusi terbesar dari kejadian tsunami adalah karena adanya beberapa kejadian longsor di Teluk Palu pada saat gempa bumi tanggal 28 September 2018. Nah, ini setelah ditarik dari hasil beberapa penelitian, Ms. Marcella mengungkapkan bahwa simulasi ketinggian gelombang tsunami dari kebanyakan model secara konsisten nilainya di bawah prediksi dari nilai ketinggian tsunami yang teramati. Kenapa? Karena pemodelan yang ideal itu membutuhkan beberapa parameter data, antara lain data hasil pengukuran lapangan, amplitude pasang surut, arrival time tsunami, dan akurasi rupture model gempa bumi, di mana untuk parameter yang terakhir masih cukup sulit untuk diintegrasikan. Dan yang terakhir, Ms. Marcella menyampaikan mengenai pembelajaran dari kejadian tsunami Palu 2018, di mana tsunami Palu sangat unik dan memunculkan pertanyaan baru mengenai tsunami yang berkaitan dengan mekanisme gempa bumi strike slip. Kemudian yang kedua diperlukan perbaikan dan pengembangan lebih lanjut untuk pembuatan model tsunami. Dan yang terakhir perlunya pembaruan terhadap sistem peringatan dini tsunami. Demikian kurang lebih poin-poin yang saya catat mengenai presentasi dari Ms. Marcella. Oke, Ms. Marcella, thank you. For next agenda, I open the discussion. Maybe first we open from directly. So anyone here want to ask directly with Ms. Marcella? Please let me know question. Okay, if no other direct question, we going to the Zoom chat, Ms. Marcella.
Yeah, so thank you for your question, Ziz. So just to clarify, so the question is about the co-seismic the co-seismic component of the tsunami and whether that was generated by a normal slip. Is that
right? Yeah, you have it right. That's correct.
Yeah, so that's a very good question. So a lot of models show that the answer is yes to that, but as we saw in the Asperity and in other models, there have been, sorry, let me just get that. Where is that? Oh, I'll find that. Yeah, sorry, I'll just find the model for you and then explain it. Oh, where has it gone? Sorry, I can't find it. Oh, here it is. Yeah, so yeah, the answer to your question is yes. A lot of models show that it is a normal slip component, but there were minor dip slip components within several of the asperities outlined. But yes, they were not enough to generate the vertical uplift of the seafloor. So yes, the major component was the normal slip for the co-seismic deformation. Okay.
Okay, I think is it clear enough? For the next question, from Brian, from Ambon Geophysics Station. Based on the movement rate of the Palu Coral Fault, how long will it take for the Palu earthquake to happen again with similar earthquake? And if their earthquake recurs with similar mechanism, does it have the same potential to cause a tsunami, or the potential is reduced because the high slope area has collapsed 2018 earthquake? There is
interesting questions. So thank you for your questions. So, okay, so So the first question, I understand you were asking about the rate of deformation along the Palu-Koro fault and whether something to do with whether this would trigger a similar kind of.
Sorry, Miss Marcella,
Yeah.
pardon me.
Which number question is it? Question 38?
From Brian,
Rian, what number? Oh,
number
there we are. I found it,
11, number 11.
11. Okay, so the question is, when can we expect another earthquake? So we can expect another earthquake would happen to the south of this area because this region already moved with 6 meters at the asperity number 3. So we cannot tell you when it would happen, but the most likely area for future Palu type earthquake would be to the north of the epicentral area, where there's been very small slip, and very far to the south, the area about 50 to 100 kilometers south of Palu city. So those are the regions where they have high stress and seismic gap. So the question was, if the earthquake reoccurs with a similar mechanism, does it have the same potential to cause a tsunami, or is the potential reduced? Well, the main earthquake of 2018 already took place beneath the bay. So, and it had a lot of slip. So the most probable outcome would be to have an earthquake not beneath the bay, although it's possible, but not very likely. The most likely outcome would be to have an earthquake away from the bay, away from Palu Bay.
Yeah, that's a really good answer, and I definitely agree with Dr. Mooney. Also, a key point is that the tsunami hazard in and around Palu, especially towards the north and south, it still remains a high hazard, and especially towards the northern, just past the epicenter here, especially where there's a sort of transform fault with the interaction between the Minahasa Trench and the Sula Block. This rapid deformation, which is about 42 millimeters per year, has actually generated really steep sloping topography in the northern area. And this has created sort of these like subsurface landslide sort of subsurface topography, which is thought to be a very high risk for further future landslides to occur. So the answer is yes, similar to what Walter has, or Dr. Mooney has said. Yeah.
Okay, Marcella, can we look at slide number 2?
Number 2, yeah.
Maybe, I'm sorry, slide number 5. 5,
yeah. Yes.
So what I notice in this map, in green is Sulawesi, and there are many bays. There are many places in northern Sulawesi near the subduction zone where you have a similar situation like Palu, where you have the shape of a bay, maybe broader than Palu. So it really reminds us that Sulawesi is a place with high seismic hazard, high tsunami hazard. And of course, Palu Bay is always going to be somewhat more worrying because the shape of Palu Bay is designed to focus the wave energy.
Yep.
Okay. Thank you, Mr. Walter Mooney and Miss Celia for your explanation. Maybe because time limitation. Next, I want to open directly question from participants. Maybe any other directly question, please let me know or raise your hands. Okay, Fajar Triharyanto. Mr. Fajar Triharyanto want to ask directly. Please, Mr. Fajar.
Hello, is my voice clear?
Yes, clear.
Okay, thank you for the chance. I'm Fajar. I work in Nabire, Papua. My question is, can you show me the map of the Asperity first, Miss Marcella?
This one?
The Asperity that contains the Asperity 1, 2, and 3. Yes.
This one? Oh, sorry.
Yes,
Yep, okay.
My question is, what data you use to generate this map, and how did you classify the Asperity 1, Asperity 2, 3, and 4? And what software did you use to produce this graphic? Because this is new to me. I'm new to this graphic. Thank you.
Okay, this is a very classic diagram. It's called by the name finite fault model. Finite fault because it has a finite length. It's not a point. A epicenter or a hypocenter is just a star. And here, can you indicate the red star? So that's just the hypocenter. But this is the amount of slip, how much motion there was on each part of the fault. So it's done by using the teleseismically recorded data and looking at the waveform. So what you will see for the Palu earthquake is that the seismic waves in the beginning, they're very weak, but after about 20 seconds, they become strong. And that is because the area that is colored red becomes a slip. This kind of diagram has been around for about 25 years and is very popular. US Geological Survey will put this model for every large earthquake on the website. So you can find it under the name finite fault model. And again, the word finite means it's not a point, no longer a point model. It's a fault model. There's another one. This one looks like a USGS web page, could easily be. The other diagram, which is very important, is that the one on the upper right, and that is the amount of energy being released on the earth by the earthquake as a function of time. As you can see, it's very clearly marked. 14 seconds, a lot of energy released. 26 seconds, low point. So welcome to the finite fault model. You can find a lot of information on the web about the method of calculation. It's based on the waveform, based on the seismic waves going to many different stations. And computer simulation. It's very well established, very well accepted, and very commonly used, and is important for seismology. Thank you. Thank you for your question.
Is it enough clear, Mr. Fajar?
How do you classify the Asperity 1, 2, 3, and 4?
1, 2, 3, and 4 is more the opinion of the author. The author looked at the finite fault, and immediately they saw very clearly region 3. Region 3 is a region with very strong motion. However, difficult to say exactly how to separate region 3 and region 4. Region 1 is to the north. It's just something to the north of the earthquake. And region 4 is small motion to the south. The central region of the fault has simply been divided into two. asperity 2, which has no very strong slip, no red zone, and asperity 3, which is the region with the strongest slip, and it has the red zone. So each person maybe will divide them a little differently. It's not so obvious.
Yes, and just to add to Dr. Mooney's point, in this particular model, the way that it has been represented is there are different components within each of them. So as I mentioned, for asperity 1 and asperity 3, both included mainly a normal slip component, but actually asperity 2, so as you can see, this connects to the North Sulawesi trench where subduction occurs, and asperity 4, this has likely been presented this way due to the geometric complexity of the fault bend towards where the rupture terminates. So there's a fault bend towards the south of where the rupture terminates, and this is for this reason why it's a separate asperity, because it's considered more geometrically complex compared to the other asperities in this sense. So different reasons for each of the asperities assigned.
Oh,
So that means that nearly everybody will get the same answer, the same finite fault, or very similar, but maybe different people will divide the finite fault into different asperities.
Right.
Thank you.
okay. One more question. What's the arrow indicate?
The slip, the direction of slip,
Direction of the slip. Oh, all right.
mostly horizontal strike slip with a little bit of a dip. You can see the dipping, downward dipping.
Okay, Mr. Fajar. Sorry, I think it is enough because the time was over. So we finish the first topic and continue with the second topic. But don't worry, for the questions did not answer, this question we will be send the question to the presenter. Okay.
Okay.
Once again, I say thank you to Ms. Marcella and Mr. Walter Muni for the great presentation and explanation. And we're going to the next topic from Ms. Ashton Woods. Ms. Woods will presenting about climate and hazard. Ms. Woods, are you ready?
Yes, I am ready.
Yeah, your time is about 30 minutes and time is yours.
Thank
Please.
you. Allow me the moment to share my screen and we'll get started. My name is Ashton Woods. I have lectured on previous days. I'm a geologist with the United States Geological Survey at Menlo Park, California, with the Earthquake Science Center. This is a continuation from day 4's lecture, part 1. So we are doing climate change and natural hazards part 2 today. To accommodate to the time changes that were made, I have reduced down the number of slides for this lecture. If you are curious about the full presentation, please refer to the recorded video that also has some supplemental videos to help understand more of the topics. So we're going to go in part 2 into climate-induced droughts and how drought conditions can cause liquefaction to become more prevalent following earthquake and seismic activity. We are also going to talk about how droughts can cause soils to become more permeable to being affected by sediment transport during flood-related disasters and landslides. So investigating in the drought trends, we look at the 2018 model, which is current updated model, showing that Indonesia, along the main islands and some of the trailing islands after Java are within the 80% drought prone rating. This means that there are some significant surface changes to the terrestrial water bodies and rivers that make it more susceptible to drought conditions following long drought seasons that occur. This also means that areas that are more drought prone, that are dealing with desertification issues, are showing issues with the peatlands becoming more exposed, releasing more CO2 into the atmosphere as it's exposed to sunlight, and carbon and methane sinks are starting to develop. We also look into these surface changes with terrestrial water bodies to talk about water stress to water scarcity. Water scarcity is becoming a major issue for Indonesia, particularly dealing in the densely populated areas, major cities, capitals. The island of Java is very susceptible to water scarcity, which is just the inability of receiving enough freshwater resources for that area, as well as changes to rivers that may be causing these surface changes to occur. We can observe this further by looking into the surface mass anomalies of terrestrial water bodies. Here we see a diagram for May 2020 looking at a global scale. We're able to see on the right-hand side where Indonesia is that it's within the green scale measurement. The units for the scale is in meters of equivalent water height, looking at the water column, and it investigates into the surface to subsurface changes that are occurring in this area. Indonesia is fairly safe in comparison to areas such as in China, Greenland, and even up in Alaska for the United States. But we see that there are some significant changes that occurred only a month later with the gravitational surface mass anomalies dealing with surface and subsurface changes in the water column, particularly at the northern part of Sumatra. These can be indicative of heavy rainfall events led by sudden drought-like conditions and the sediment transfer of different riverine bodies pushing sediment off into areas where it can't be properly transferred, thus causing the surface changes to present. We're able to investigate into vulnerabilities as well. When we look into subsurface groundwater changes, most of these are occurring near the plantations and agricultural zones. These areas are experiencing more susceptibility to flood-related disaster, coastal damage following tsunami and typhoon events, dealing with more potential fire-prone areas that can occur during drought-like conditions. And there is also the possibility that seismicity can cause subsurface changes within the groundwater areas and in the aquifers that could potentially cause more sinkholes, more sediment transfer, the possibility of secondary disasters such as liquefaction events to occur, and more landslide susceptibility. We see this further by looking at a seismicity hazard map that was put together by the Jim Foundation in 2018, looking at the peak ground acceleration. The peak ground acceleration doesn't measure into magnitude or size. It's more about the maximum acceleration of the ground that is experienced during the actual seismic event. I wanted to include this in relation to the previous slide to show that there was some strange similarities that were starting to occur, particularly around the measurements of peak ground acceleration for the blue and the green areas on this map. It's not unusual to see it around the Sunda Arc and the Banda Arc of having high levels of peak ground acceleration following seismic activity. However, these blue and green areas are in areas where seismicity is causing surface and subsurface changes to occur and more liquefaction events to occur. And I found it interesting that it directly correlated with, again, the previous slide, where there there is evidence of groundwater changes that are occurring because of the amount of human activity that is in these areas. We look further into surface changes as well. Surface changes can be caused by tectonic evolution, geodynamic forces. It can also be caused by fluvial hydrology, and through different types of disaster-related events. And it can even be induced by anthropogenic causes, such as digging wells and draining of aquifers, causing sinkholes to occur in certain areas. This allows the cities, particularly in Indonesia along the deltas, to undergo sinking. And when you take this into relation with sea level rise, it causes more potential for flood-related and tsunami disasters to impact coastal cities and regions. This was a supplemental diagram that I had created for a video that I included in the original lecture. However, again, because of the time, I wanted to make sure that I just covered it real quick and not play the video. You're able to view the video further on the recorded lecture for this presentation. This is basically explaining the potential of soil saturation and what happens with certain types of different soils and vegetation in a given area and how that can contribute to runoff. We see for number one, there's no vegetation and the soil profile is overtilled. There's too much exposure that has happened to the soils within that area. And so there's a significant amount of sediment transport and runoff, as we can see here in B, whereas there is very limited infiltration into the groundwater. And so A is empty. And then we go to the other side of the spectrum, which is number 4, where there is natural vegetation, there has been little stress dealt to the soil itself. There's no anthropogenic consequence, and even during natural occurrences such as drought or heavy rainfall, we see that the ground infiltration into the groundwater, we see that it's normal with very minimal runoff potential. However, too much infiltration can lead to soil saturation. So even though it has more protection against runoff of sediment, especially along the surface, it still has the potential to cause flash flooding should it become oversaturated. This is an erosional map of watersheds with highest risk of erosion. The highlighted sections are the top 10 countries in the world based off of 2020 data of being the most susceptible to erosional forces near watersheds. And it was very curious to see that Indonesia accounts for 3 of the ranks in the top 10 countries. The amount of erosion of these sediments can lead to processes of eutrophication, nutrient runoff, turbidity, and terrestrial water sources, and can eventually cause a tertiary disaster, which is known as harmful algae blooms, that help to contribute to the potential of primary and secondary disasters should one follow after a harmful algae bloom occurs. I won't spend too much time into harmful algae blooms just to maintain consistency with the topic, but it is important to mention it as the harmful algal blooms themselves allow for marine and freshwater resources to diminish in health. And when these areas do not experience health, there can be natural barrier die-off, which leads to more disaster prone and disaster vulnerability in the future. Harmful algal blooms, again, they can occur in freshwater sources, lakes, they can happen on rivers, it can occur during heavy snowfall if there's enough of the cyanobacteria present. It's also possible along lagoons and on coastal waters near beaches. We see the effect of harmful algal blooms and how it contributes to the die-off of natural barriers. When the harmful algal blooms are developing themselves, they respirate CO2 into the atmosphere. The sunlight is unable to penetrate past the harmful algal bloom, which causes no light penetration to happen beneath the areas where the harmful algal bloom is taking place. And as the harmful algal bloom begins to decay, because as it's a natural ecosystem of organisms and cyanobacteria, it causes it eventually will decompose. And when it decomposes, it releases a tremendous amount of methane into the atmosphere as well. It also diminishes the amount of oxygen within these environments, which creates hypoxic zones. And these hypoxic zones are areas where there's very little oxygen for ecosystems to maintain their health. And so they eventually die off. So now I want to go into a different consequence of drought-related issues and how harmful algal blooms can contribute to seasonal variations that also cause issues with desertification. This is an image of a plantation in the Kalimantan region in on the island of Borneo. We see here that this is very barren area. There's no vegetation at all. The soil is entirely exposed to natural and outside sources, and there's these white deposits that are occurring, and this is known as soil salinization, which is a major consequence of desertification. Alien erosion is particularly damaging for desertification in these areas. Indonesia experiences deflation specifically, which can cause erosion all the way down to the water table as sediment is being transferred through aeolian processes several hundreds of kilometers away. This can cause infrequencies in storm variation and intensity, and it can also cause these areas to become more susceptible to seismic activity, leading to secondary consequences such as more landslides. Liquefaction is particularly damaging in these areas, and it can also even lead to mud flows and severe flooding incidences following heavy rainfall. And again, this is primarily driven by desert or deforestation. Nutrient leaching also becomes an issue in these deforested areas that are undergoing desertification processes, where the soils are having all of the nutrients come up to the surface level and causing it to make the land less fertile and to become barren. This goes again into soil salinization, which is when the salts within the earth become so consolidated that it has nowhere else to go, especially in areas that are drought prone, where there's been little moisture infiltration into the soil itself. And so the salt comes up to the surface, and this prevents any sort of soil fertility to happen, and these areas become large regions for liquefaction events to become more prominent following several different types of natural disasters. Tsunamis are also particularly responsible for soil salinization, especially along coastal regions. We see at the bottom that during a tsunami event, the saline seawater comes in and infiltrates brackish groundwater into the groundwater table. And so there is freshwater mixing in near coastal areas where lagoons and wetlands are present, and the fresh groundwater is being infiltrated by the brackish groundwater. So following the tsunami event, as the waves are being pulled back into the coastal waters, as we see here up in the top diagram, the groundwater and the lagoon and wetland area has now become saline groundwater, which causes these areas to undergo salinization. On an opposite spectrum, another contributing factor to consequences leading from desertification and drought-related conditions is soil compaction. This is a quick diagram of annual changes throughout the year. There's very little change in the soil moisture daily climatology for Indonesia. However, as we get more into the late summer and fall months, we start to see that there are some regions that are losing their soil moisture content. When the changes of soil moisture content happen, soil compaction can occur. The pore spaces become reduced and runoff potential becomes more extreme in these areas. There's a significant amount of sediment that can be lost during soil compaction following heavy rainfall that follows shortly after drought-like conditions. It's not unusual to see drought conditions and then that lasts for about maybe several weeks to months, and then suddenly having extreme heavy rainfall that leads to flash flooding and mud flow events to occur. This is a very normal occurrence throughout the entire world, particularly in the southern hemisphere, and Indonesia is no exception to this sort of climate impact. The amount of soil that runs off into coastal waters can cause variations in sea surface salinity. Here I have data from 2015 to 2019, but I started it in 2018. So we can take a pause here and observe the sea surface salinity levels here in Indonesia for 2018, showing that they are relatively low, especially around the coastal areas. So these are more brackish areas. However, the normal PSU unit for brackish water to freshwater is 30. So it's still fairly saline around this area. As we run its course to 2019, we'll start to see changes, especially on a global scale. And now we see there are areas like here where the sea surface salinity has actually risen, showing that these areas have become more saline, possibly following tsunamigenic or tsunami-related incidences that have occurred, as well as dealing with certain turbidity issues following soil and sediment transport into marine and coastal waters. We can look at this. Oh, my apologies. Video had a mind of its own. We can see this further for information for August 1st, 2020 to August 3rd of 2020, looking at sea surface salinity and changes that followed following flood-related disasters and tsunami-related disasters. For this particular incident, however, I chose to focus on two different flood events that happened, one off the coastline of Sumatra, as well as one that happened on the island of Borneo. We can actually see here that there is some heavy sediment transfer that's happening from the river system from flooding within the Kalimantan region, bleeding out into the coastal water. And this area here is where it has fallen below the recommended level for sea surface salinity and is causing the coastal waters to become more brackish. We see that here also in Sumatra. However, this wasn't necessarily a heavy flood incident. This was purely just high tide coastal flooding that only went a few feet inland and caused very little soil to be flooded out into the ocean, the actual coastal waters. A few days later, showing how it has worsened over time. This is August 4th to August 6th of 2020, showing again that the high tide event caused very little changes in the sea surface salinity. However, the heavy flood event that happened that drained out through the river here along the coastline has now caused the southern coastline to also experience brackish water mixing along the coastal regions, which creates ideal conditions for harmful algal blooms to occur and can cause hydrophilic vegetation along the coastline to start to become less prominent in those areas should this brackish coastal water continue. And then ultimately with changes of sea surface salinity, there is also the possibility of sea surface temperature changes. The scale here is measured in Kelvin. And for 2018, we see that Indonesia is fairly high on this information here for sea surface temperature. That's not entirely surprising for the current climate that we're experiencing today. And as you can see, this is a wide distribution across the entire southern hemisphere where the waters are much higher in temperature. This was an interesting phenomena to experience for 2019 off of the coastline of South America. This is actually El Nino effects taking place, causing the drought-like conditions that followed at the end of 2019 to the beginning of 2020, and then eventually led to the sudden rainfall and flash flooding events that occurred for the majority of Indonesia at the beginning of the year of 2020. So we go into El Nino Southern Oscillation, which goes through the phases of La Nina to El Nino and neutral ENSO. Normally during neutral ENSO, Indonesia experiences normal seasonal variations of wet to dry seasons. There's less subsidence runoff and changes within the coastal waters for Indonesia. However, during El Nino phase, Indonesia starts to undergo extreme variations of wet and dry seasons, particularly drought-related conditions that are contributing to their climate impact. The convection forces are heading more towards South America, and this can also cause significant sea surface temperature changes and sea level changes over time. And to summarize up on climate change, part 1 and part 2, and it's more than just greenhouse gases that we should take into consideration the effect of greenhouse gases on the and their influence on disaster frequency as well as disaster intensity, as it makes the environment more susceptible to disaster prone related issues. Storm potential can very much increase, and coastal regions are extremely vulnerable to tsunami and high tide events, as well as riverine flooding. And all of these surface changes can lead to prolonged droughts, which make it more susceptible for Indonesia to deal with liquefaction and landslide potential in the future. If this continues, these trends are expected to get much worse by the year of 2050, and there must be some serious consideration into the mitigation tactics to include climate change impacts in the policy decisions and into the mitigation techniques in order to become more disaster resilient in the future. Thank you all for your attention.
Okay. Thank you, Ms. Woods,
Yes.
for the nice and very interested presentation. I will give the notes about your presentation in Bahasa. Is it okay?
Yes, of course. Thank you so much.
Baik, peserta diklat, pada pagi hari ini pembahasan sesi kedua ini lebih banyak berkaitan mengenai iklim dan dampak yang ditimbulkan dari perubahan iklim tersebut. Catatan saya di sini hanya ada beberapa, di mana Miss Woods membahas mengenai perubahan iklim yang memberikan dampak antara lain itu tadi meningkatnya polusi dan penyakit, kemudian perubahan iklim dapat menyebabkan kekeringan yang mengakibatkan akhirnya gagal panen, dan juga perubahan cuaca di mana variasi musim dan cuaca yang tidak bisa diprediksi. Kemudian tadi Miss Woods memaparkan mengenai bencana kekeringan, ditampilkan peta pemodelan di tahun 2018, di mana di situ dijelaskan 80% wilayah Indonesia ini rawan kekeringan, dan juga adanya peningkatan intensitas kebakaran. Kemudian pada bahasan berikutnya dijelaskan mengenai kelangkaan air. Kelangkaan air di wilayah Indonesia khususnya ini berkaitan dengan kondisi padatnya jumlah penduduk, kemudian kondisi yang ekstrim, dan adanya perubahan permukaan tanah. Bisa dilihat juga dari tadi peta, ditampilkan peta groundwater stress, di mana yang saya tangkap itu groundwater stress itu adalah pengukuran rasio air tanah relatif terhadap tingkat pengisian ulang di atas akuifernya, gitu. Dan kemudian Miss Woods membahas mengenai perubahan atau penurunan permukaan tanah yang salah satunya disebabkan juga karena kejadian gempa bumi, di mana penurunan permukaan tanah tersebut juga dapat mengakibatkan kenaikan muka air laut. Kemudian dijelaskan mengenai pengaruh vegetasi terhadap kualitas dan ketersediaan air tanah dan sedimentasi, yang tadi bisa kita lihat dari adanya 4 simulasi terhadap kondisi tanah untuk kondisi tanah masing-masing yang ditanami dan yang tidak ditanami, hasilnya berbeda, gitu. Dan tadi juga Miss Woods menampilkan mengenai peta resiko tinggi terjadinya erosi di daerah aliran sungai, di mana kalau kita lihat dari petanya tadi, wilayah Jawa, Sumatera, dan Sulawesi itu mempunyai risiko tinggi untuk terjadinya erosi di sekitar daerah aliran sungai. Kemudian mengenai isu iklim, Miss Woods juga menjelaskan mengenai ledakan populasi ganggang atau tadi harmful algae blooms, di mana itu bisa terjadi di laut, di sungai, ataupun di danau, dan dapat menyebabkan kerusakan lingkungan, serta terganggunya siklus hidrologi. Lalu Miss Woods menjelaskan mengenai degradasi lahan. Tadi ada istilah aeolian erosion. Mungkin ini baru buat kita ya, tapi kalau saya yang sedikit saya pahami, aeolian erosion itu adalah erosi yang disebabkan oleh aktivitas angin, di mana jenisnya dari aeolian erosion itu ada deflasi dan juga abrasi. Deflasi itu proses terlepasnya tanah dan partikel batuan yang terbawa dari angin, sedangkan abrasi adalah proses penggerusan batuan oleh partikel-partikel yang terbawa angin. Kemudian yang kedua ada deforestation atau penggundulan lahan, di mana kondisi penggundulan lahan ini itu akibatnya adalah kerentanan terhadap lingkungan, kemudian dapat meningkatkan frekuensi bencana longsor, dan mengakibatkan tanah menjadi kehilangan nutrisinya. Dan tadi juga yang ketiga dijelaskan mengenai salinitas tanah. Salinitas tanah itu adalah peningkatan kadar garam dalam tanah. Ini mengakibatkan tanah menjadi terkontaminasi sehingga menghambat pertumbuhan tanaman. Salah satunya salinisasi tanah ini bisa disebabkan pada saat akibat tsunami, yang dimana di slide berikutnya tadi dijelaskan bagaimana proses salinisasi tanah pada saat kejadian tsunami berlangsung. Kemudian kemudian yang keempat itu mengenai pemadatan tanah atau soil compaction. Soil compaction ini menyebabkan pori-pori tanah menjadi berkurang sehingga adanya potensi limpasan permukaan, di mana aliran air di atas permukaan tanah ini menjadi frekuensinya lebih tinggi karena berkurangnya penyerapan ke bawah, dan ini tentunya dapat mengakibatkan bencana yang lebih lanjut seperti banjir gitu, karena berkurangnya penyerapan. Dan juga tadi ditampilkan mengenai diagram sea surface salinity dalam satuan PSU, di mana diagram si surface salinity ini menggambarkan tingkat keasinan atau kadar garam terlarut dalam air. Tadi ditampilkan fokus dari si surface salinity itu berkaitan dengan kejadian banjir di wilayah Kalimantan dan Sumatera, di mana kita bisa lihat adanya peningkatan debit air atau banjir di dua wilayah tersebut itu mempengaruhi tingkat si surface salinity, di mana kadar airnya itu menjadi lebih payau pada periode waktu tertentu. Dan yang terakhir tadi yang saya tangkap, Miss Woods menjelaskan mengenai ENSO. Mungkin sebagian sudah sering mendengar istilah ENSO, tapi mungkin kita tidak memahami terlalu dalam karena itu memang lebih banyak dibahas di bidang ilmu meteorologi atau klimatologi. Tapi yang saya tangkap sedikit mengenai ENSO atau El Nino Short-Term Oscillation itu adalah fenomena pola iklim yang mengakibatkan perubahan suhu perairan dan atmosfer di bagian timur hingga tengah Samudra Pasifik. Itu ENSO itu ada 3, keadaan ENSO hangat, keadaan ENSO dingin, dan ENSO netral atau kondisi cuaca normal, di mana pengaruhnya terhadap Indonesia dari kejadian ENSO ini adalah terjadinya El Nino atau ENSO hangat atau peningkatan suhu di Samudra Pasifik. Nah, ini mengakibatkan penurunan curah hujan yang terjadi di wilayah Indonesia, kemudian musim kering yang berkepanjangan, dan juga menurunnya temperatur permukaan air laut di Indonesia. Oke, itu tadi beberapa catatan yang bisa saya tangkap dari presentasi Miss Woods. Oke, thank you again for Miss Woods, and now time for discussion. Anyone here want to ask first directly with Miss Woods? Please let me know or raise your hands. And also in Zoom chat, we have question for you, Miss Woods.
Yeah.
Maybe I try to read it one by one. The first question, question number 49 from Sandi Trigustono. Can we also take into account this COVID-19 pandemic or any other disease and its evolution as an effect of climate change?
Yes.
Could you understand about the question?
Yes, I can. And I actually know quite a bit about this. My husband is actually a public health specialist, and he has worked in collaboration with the United States government and the CDC. And we normally look at some of my geological data in relation to his public health findings. So I am very excited to have the opportunity to slightly talk about this. I won't go too far in the detail because we do have time restrictions today. But I can definitely say dealing with diseases, the susceptibility of climate variations, especially dealing with drought-like conditions, allow for disease potential to steadily increase. This is mostly due to the fact that diseases like coronavirus or the COVID-19 pandemic that's happening right now is capable of maintaining presence on surface areas and can also transfer through vector transfer, which also deals with, it can primarily deal with mosquitoes and things like that, but we haven't found evidence of COVID-19 in mosquitoes as of yet. Animal transfer, however, is significant, and we definitely know that coronavirus is capable of being transferred from animals to humans through simple mucous membrane processes or during issues with like if an animal goes and has marked its territory in the woods and it happens to be infected, that area is now capable of consolidating COVID-19 virus within the soil in that area, making the soil less safe. So when we take into consideration climate and climate variations, the actual process of again with droughts and things like that and rainfall, we see that COVID-19 has a far more substantial reach of entering into terrestrial water sources that people tend to drink from, and it can also affect the soil into making the soil and the vegetation and other animals very sick. Again, I can't go too far into it because of time restrictions, but I would love the opportunity to talk more about this possibly in the discussion, and I'll be more than happy to put this in a Word document and go further into the science behind that. I also want to point out real quick, I believe there was actually a question before number 49, from before Sandy, from Bayou Granada, number 18, dealing with INSAR and tsunami early warning systems, but I'm not certain if that was for me or if that was more for Marcella.
Okay, Miss Woods, maybe the question from Bayu is for Marcella, and we send letter in LMS. Okay. We continue to the next question.
Yes.
There is question number 7 from Asher Octave.
Mhm.
Would you explain about the correlation of SST and sea surface salinity against precipitation level?
Yes, of course. So dealing with sea surface temperature and sea surface salinity with precipitation, when we take into consideration precipitation, we must also consider what the atmospheric gases and the equilibrium of the gases in the atmosphere for that geographic area are currently. So say there was a volcanic eruption that happened, again with we'll reference the 2018 Anak Krakatoa eruption. Say that erupted, it released SO2 into the atmosphere. Then we can take into consideration that there was some acid rain that possibly took place over the marine waters in the sea between Java and Borneo. When we look into that and the acidification process from the acid rain that could occur from volcanic eruptions, it would cause surface salinity changes as the ocean is undergoing acidification processes, because there is some mixing depending on how long the actual precipitation event has occurred. And that can ultimately cause sea surface temperature to change and rise steadily as sea surface salinity also is being affected. And so ideally, the correlation with precipitation levels dealing with sea surface salinity and sea surface temperature is that the sea surface temperature, as it increases, there is the possibility that sea surface salinity will also increase following precipitation events, depending on the chemical influences in the gases in the atmosphere during that time.
Okay, thank you, Miss Woods. Maybe before we continue to Zoom chat, any other here want to ask directly with Miss Ashton Woods? Please let me know or raise your hands. Or if you want to give experience, about the climate issue. Anyone here? Okay, yeah, yeah, from Mr. Eddie Santoso. Hello. Hello.
Dedi.
Oh, sorry, Mr. Yeah, hello, please, Mr. Dedi.
Yeah. Okay, thank you, Mr. Aston. My name is Dedi Safari. I am from the Earthquake and Tsunami Mitigation Division. Talking about the climate change, I want to ask about the relation between climate change and anthropological factor. In your opinion, what's the factor are more dominant in causing the climate change? What's the climate change is natural process or it's more causing by anthropological factor? Okay, thank you.
Yes, of course. That's a great question. So as I mentioned in part 1, there are climate variations that we can track through the paleoclimatology of the Earth. It's a natural thing that occurs, variations in high levels of temperature, so mass heating to mass cooling. But with our current climate change conditions that we are experiencing, it's a combination of both natural processes and anthropogenic processes. The anthropogenic processes that are contributing, however, are very minute in comparison to what the climate is just naturally doing. It's more of a problem for disaster intensity and disaster frequency, which contributes, which is being contributed to by anthropogenic causes. So the more densely populated an area is introducing different types of chemicals into the atmosphere and into the environment, or causing surface changes for urbanization projects, the more susceptibility that the disaster frequency and disaster intensity will increase in those areas in relation to what is already happening in our current climate. So I would definitely say, for the sake of disaster vulnerability, it is a combination of both anthropogenic and natural causes that are contributing to the climate change issue that we are experiencing. Was this a clear enough explanation?
Mr. Debbie?
Yeah, it is clear.
Is it?
Thank you.
Okay,
cool. Thank you.
Thank you. Is there anyone here want to ask directly with Ms. Woods? Okay, maybe we go back to Zoom chat again.
Yes.
I will read question number 20, Ms. Woods, from Eddie Santoso. Is there an effect on fisheries conditions in Indonesian waters related to increased salt levels in the sea due to climate change? Maybe the question is you can understand.
Yes, definitely. And I actually do know how to answer this one. So I try not to look too much into fisheries normally, because it's often more of a government sector problem, more so than it is a researching problem. However, I have looked into it. The current conditions of sea salinity levels changing due to riverine flooding, causing turbidity in the coastal regions, and causing some brackish water to emerge following the flood-related events, actually can cause the areas on the coastlines that are ideal for certain types of ecoregions where fisheries are, or fishing areas are designated. It's actually causing these areas to undergo various changes. There's a indication of coral reefs that are starting to undergo bleaching effects because of the acidification of the ocean in those areas along the coastal regions. And there's also a decline in the clam and other type of calcium carbonate organisms in that area because of the sea salinity changes that are occurring. So following flood-related disasters and tsunamis where they're pulling more debris out, or whenever fresh water is introduced and causing brackish water mixing, these areas are actually being directly affected. So yes, there is a relationship between the two.
Okay, good explanation, Ms. Woods. Maybe just one more question, because our time is limited.
Yes.
One question, last one question. Question number 3 from Agung Saptaji. He saw about map surface. He saw about surface temperature by satellite. Is the observation by satellite real time or minute to minute? And the second question, if we correlate surface temperature some location with earthquake prediction, is that possible? because when shallow earthquake energy stress increase some location before event, the surface temperature will follow increase too. Maybe it's your opinion about correlated about the earthquake and increasing surface temperature. Please, Ms. Woods.
Yes, definitely. So for the first part of the question, yes, the map was in real-time data. It was for the sea surface temperature for satellite. And this was obtained through the national, through NASA, with the United States. Dealing with the second part of the question, when we correlate surface temperature to earthquake prediction, we can definitely see surface temperature changes following earthquakes because of the amount of acceleration and velocity that's happening around that area as seismicity is occurring. And this will ultimately cause frictional forces. This goes into some basic geophysics as well as some basic physics about when you have frictional forces happening upon each other, it can actually produce heat. And so it's not unheard of that during seismic activity, we can actually see the surface temperature change. Now, by the time the surface temperature has already changed, this means that the seismicity in that area has already reached a point where we should probably have noticed the actual, we should have seen the actual earthquake damages start to occur depending on the size of the magnitude and the peak ground acceleration of that area. So by the as a prediction model, I probably wouldn't suggest looking at soil surface temperature and sea surface temperature and predicting a earthquake potential. I don't know, Dr. Mooney, do you have any contrary information dealing with that?
Yeah, so the temperature change caused by an earthquake is concentrated on the fault plane. And the fault plane can even get to the temperature of very, very locally melting the rock, caused by the friction. But as you move away from the fault plane, the temperature increase drops very rapidly. Furthermore, we cannot use any temperature, we have not found that any temperature change can predict an earthquake because there are larger temperature changes due to sunlight and hydrothermal effects. So earthquakes cannot be predicted by looking at temperature neither in the ocean nor on land. Thank you.
Thank you, Dr.
Thank you, Ms. Ashton Woods and Ms. Walter Mooney for explanation. I'm sorry, but the time is over. I think enough for first session this morning. Once again, I say thank you to all speakers from USGS and also to all participants. And don't worry for the question didn't answer. You can check the LMS account maybe regularly because the TSO will post your question before in LMS. Thank you. Okay, now we take a break for 5 minutes, and then for next session we'll guide by Mrs. Octavia, and she was here, Miss Octavia, and we start again in maybe in 9:20 or 9:25 maybe. Okay, I think enough for today. Thank you for your attention. Good morning. Assalamualaikum warahmatullahi wabarakatuh.
Thank you all. See you all after the break.
Good morning, everyone.
Morning.
Morning. My voice is clear?
Yeah. Okay.
Yes, it's clear.
Okay. Good morning, Miss Jessica. How are
Good
you?
morning. Well, thank you.
Okay. Can we start the presentation right now?
Yes. Hello,
Is
everyone.
every yes. The I will ask the participant first. Is there? Are you ready, the participant, for the next session? Uh, okay, I think the participants is already yet. Okay, can we start the presentation right now, Miss Jessica?
Yes.
Okay, okay. So allow me to introduce myself. My name is Nur Hidayati Octavia. I am from Seismological Engineering Department in Biology and BMKG. I will serving as your moderator today, substitute Mrs. Audia Kaluku. Before we start the presentation, I would like to inform you on the agenda for this session. The presentation will be delivered in two sessions and concluded with the discussion session. Our first presenter is Ms. Jessica Reed. She will present earthquake in the liquefaction. And our last presenter is Mrs. Aston Woods. She will present the hazard mitigation. For our presenter today, we apologize because some participants maybe have to leave the Zoom meeting earlier because they have to have Friday players. Due to the time limitation, allow me to state the regulation for the session. Each session we have 40 minutes to presentation and followed by 10 minutes for discussion. So for the participant, please use the Zoom chat. Please state your name and affiliation. We will take a note the question and pass it to the presenter. Sorry. No. Welcome to our first presenter, Miss Reed.
Hello,
Time
everyone.
is yours, Miss Reed. Yeah.
Okay. My name is Jessica Reed, and today I'm very pleased to talk with you all about earthquake-induced liquefaction. In some earlier lectures, we've talked about liquefaction already and how it can be caused by landslides and earthquakes and really any kind of pore pressure increase situation. I went over an example of specifically flow liquefaction induced by a landslide in Oso, Washington. And in this lecture, I'm going to focus on a new kind of liquefaction called cyclic liquefaction, which is induced by earthquakes. So this distinction between these two kinds of liquefaction is primarily in the loading mechanism. In flow liquefaction, we talked about how there would be a single shearing event, like a landslide. And in order for liquefaction to occur, you must have a shear stress that's greater than the strength of the material. This can cause landslides that are very catastrophic, move very quickly, and are very hazardous to human life. Cyclic liquefaction can happen more easily. This is because the duration of the shearing event is longer, and stress reversals involved in earthquake shaking can actually cause the pore pressure to increase with every cycle until a failure event. So cyclic liquefaction happens more often, and it's not as catastrophic as events involving flow liquefaction, but it can be very damaging to infrastructure and also cause loss of human life. Oh, here's a fun animation I did. Cyclic liquefaction and flow liquefaction are similar in the basics of soil strength and pore pressure. You still need wet, loose sediment with high porosity, and that sediment has to settle or compact during earthquake shaking in this case. And that would increase the pore pressure, which would reduce effective stress and compromise the strength of the material. But there are two main ways that cyclic liquefaction can differ. And the first is that since the initiating force is sustained during earth shaking, greater liquefaction effects are achieved with smaller shear events, which alone wouldn't have caused flow liquefaction. And secondly, earthquake shaking is regional, whereas landslide initiation is often localized, each landslide. And so this kind of cyclic liquefaction can occur over larger areas and actually can occur in layers below the surface. And this can manifest in some really interesting ways. For example, this picture on the right shows a house sinking into the ground in San Francisco during the 1989 Loma Prieta earthquake. And you can see that some ground beneath this house appears to have liquefied and lost its strength. This is the same thing as you saw on the other slide. Liquefaction destabilized these buildings during the 1964 Niigata earthquake in Japan. And although this phenomenon of liquefaction had been observed before 1964, it's notable that this event, along with the 1964, same year, earthquake in Alaska, they really gained a lot of interest in liquefaction and worldwide attention. And that was kind of a turning point in the study of liquefaction and understanding that this is a really common thing that accompanies earthquakes. Another way liquefaction can appear at the surface is as sand boils. We've talked a little bit about this throughout the week. This is also from the Loma Prieta event in California in 1989. Sand boils occur when a sandy layer of soil, it must be wet and sandy, that is susceptible to liquefaction, is overlain by other layers of material, silt and clay. And these act as kind of a trap. When the ground motion of an earthquake causes the soil to compact and settle, the saturated layer of sand below is essentially compressed by the overlying layers, and the trapped water is put under some pressure. This liquid tries to escape, and naturally it flows upwards in the dike. Excuse me. For some reason, my computer shut off. There, the dike that you see up in the upper right figure. And this kind of spews sandy water up onto the surface in a sort of volcano. This is a perfect example of a sand boil that's been lithified, and it's actually broken open so you can see a cross-section of what it looks like. Notice the sand dike coming up and forcing apart the layers above it. Another feature of cyclic liquefaction is buoyancy. Since the sand below or the material below acts as a liquid, this causes redistributions according to relative density of objects. You see this sewer has buoyed up as a result of liquefaction in Niigata, Japan. The flip side of this is that denser objects, if they are resting upon material that is liquefied, can also sink. And there are some accounts of surprising things sinking and floating in these earthquake events. This is a picture of lateral spreading, and lateral spreading is is a very common and extremely destructive form that cyclic liquefaction can take. And it's particularly damaging to rigid materials and large infrastructural features like roads and bridges and pipelines, lifelines. And what happens is you'll have a liquefaction susceptible layer underlying more rigid layers and perhaps cement or a rigid man-made structure. And when liquefaction occurs, the liquefied underlying layer will flow somewhere, maybe due to gravity. And this will cause the overlying rigid layers to kind of go with it, and they'll pull apart or crunch together depending on where that liquefied layer underneath is going. Here's another example of lateral spreading that has actually pulled apart this bridge in the 1964 Niigata event and caused the sections to collapse down. So I've framed this discussion of flow liquefaction triggered by landslides and earthquake liquefaction, cyclic liquefaction triggered by earthquakes. But we know that these geohazards are really interrelated, and you can have an earthquake that causes a landslide that might cause flow liquefaction, but also there's evidence of other liquefaction on the ground. And so we're going to look at a couple of examples of real events that occurred. This is the Sichuan province 2008 Wenchuan earthquake. It caused thousands of landslides. You can particularly see the high density of landslides near this river. And around 20,000 people were killed by the landslides alone triggered by this earthquake. These landslides were so intense, in fact, you can see they've blocked off several areas of the river and created lakes. This area is really susceptible to landslides. It's a very steep region with high seismicity and high rainfall. So it wasn't surprising that landslides would be triggered by an earthquake event. But we also saw evidence of cyclic liquefaction. The upper right-hand figure is a less perfect, but still an example of a sand boil, where you see this sandy material has spewed up out of that hole and over the grass. There's also evidence of ground settling during the earthquake, which often causes these kinds of sand boils. And you can see it's separated the buildings. On September 30th in 2009, a magnitude 7.6 earthquake occurred off the coast near Padang and killed over 1,000 people and triggered massive landslides that you can see on the lower left. These landslides actually accounted for about 2/3 of the fatalities in this event. And it just shows that landslides can be extremely catastrophic. Although earthquake generated like cyclic liquefaction can be very destructive, it's often the landslides that cause the highest number of deaths. The graph on the lower right shows a rainfall intensity in the time leading up to the earthquake and landslides, and you can see high amounts of precipitation beforehand. This may have allowed landslides to be greater and more mobile or caused liquefaction within these landslides, like flow liquefaction. The upper right figure, you see the little red dots on the map. Those represent the landslides that occurred. And you'll notice they're all pretty much clustered around that tan color, which is quaternary volcanic rocks. And there have been some studies about the effects of earthquakes on liquefaction within volcanic deposits, not just sandy deposits. So that's an interesting area of study. On October 8th, 2005, a magnitude 7.6 earthquake struck northern Pakistan. The event killed tens of thousands of people and triggered several thousand slope failures. These failures were mostly rock falls and rock slides, but the event also caused liquefaction, and evidence was found, as it often is, in the form of sand boils. Here they're called sand blows, but it's the same thing. And on the left, you'll see a little cartoon diagram of the image on the right. And you might notice the familiar vent, the sand dike that is pushing water and sand up towards the surface in a volcano shape. Liquefaction susceptibility is an important assessment, especially in areas where liquefaction has occurred or is expected to occur based on proximity to rivers or coasts or the type of material that's deposited there. This is a liquefaction susceptibility map for part of the Bay Area near San Francisco. You see the colors correspond to the level of susceptibility. The picture I've included is another example from the Loma Prieta earthquake and just shows that this earthquake produced a lot of cyclic liquefaction, and we saw this in the case of sand boils, lateral spreading, and buoyancy. And it's really no surprise that this area is very susceptible to liquefaction, and we should monitor it in the future. And one way people do this is, it's very useful, but it's a little bit time intensive, is by looking at individual units and assessing their specific susceptibility. The y-axis here shows the age of the units, and the x-axis shows the type. So you can see on the left, artificial fill is one of the most susceptible units to liquefaction. And San Francisco has a lot of, is built over a lot of fill. Also susceptible are sands and alluvial fans. And also notice that as these units get older, they become less susceptible to liquefaction. Although this kind of field examination and analysis of map units is really important to a detailed understanding of liquefaction susceptibility, it's not often practical. And there are usually areas where this is impossible, or it's impossible to know before liquefaction happens. So there are ways of modeling it. The USGS Earthquake Hazards Program uses a model based on the work of Zhu and others from 2017. This takes inputs from environmental factors like distances from coast and river and water table depth and mean annual precipitation. Notice it doesn't take information about the rock units yet, and that's kind of a drawback. It also takes information about the peak ground velocity and shear wave velocity, so about the specific earthquake that might occur there. And then it generates a general probability map and the exposure, possible exposure to humans. And this is good for a broad understanding of what might occur, but it's not as useful to construction projects or other things like that as a detailed soil analysis. if necessary and if possible, there are methods to improve soil stability and reduce the chances of earthquake-induced liquefaction. There are different methods of soil improvement, and the list I've drawn on the upper left of this slide kind of cover the main ideas behind these methods. You've got densifying the soil, you've got draining the water out of it, reinforcing it, or compensating for the material. There are actually some things where you remove material and put in other material that is less susceptible, and also confining it so it cannot flow. The image on the top is, if you're interested in looking at exciting videos of this kind of thing, I recommend this method, which is called dynamic compaction. And it's dropping a weight about 10,000 to 40,000 kilograms from a height in free fall, and to kind of, and it creates this grid pattern. They go through a couple of different times. And the idea is that if you compact the soil, if you pre-compact it and reduce the pore space, then liquefaction can't be as dramatic during an earthquake event. Another thing you can do is construct more stable buildings by using end-bearing piles instead of friction piles. A friction pile would rely on the soil around it to hold it in place. But we know that if liquefaction occurs, that soil will be flowing and the pile will flow right with it, or it'll sink. But an end-bearing pile actually affixes itself to something that is not susceptible to liquefaction. And so those kinds of piles will hold up better and produce more stability for their buildings. And there are a bunch of other methods like adding grout or jagged gravel that won't rotate. And this is the work of geotechnical engineers. But I really want to emphasize that often this is impractical. It's very expensive, and usually decisions are made to relocate or minimize the utilization of liquefaction prone areas. So a quick summary of what we've talked about. We looked at some impressive examples of cyclic liquefaction, how we learned about how it can occur when flow liquefaction cannot, because the duration of an earthquake and the stress reversals involved in ground shaking can allow pore pressure to build up. We looked at buoyancy and sand boils and the destructive lateral spreading that occurs. And we looked at how cyclic liquefaction and possibly flow liquefaction can be evolved in the same earthquake landslide events. And I briefly covered liquefaction susceptibility mapping with map units, or modeling based on more generalized variables, and introduced the idea of improving the soil strength artificially. And with that, I want to thank you very much for having me this week, and that's all I have.
Okay, thank you for Ms. Reed for the nice presentation today. We go to the discussion session, I think. Okay, it's okay?
Yes.
Okay. So for the participant, there is any question for Ms. Reed about the? I'm sorry. I'm sorry. I think I have a few summary about your presentation. I will convey in bahasa. Is it okay for you?
Yes, please.
Okay. Untuk presentasi Miss Reed hari ini, beliau membahas tentang gempa yang dapat memicu likuifaksi, di mana likuifaksi disebabkan oleh yang pertama adalah adanya tanah longsor, yang kedua adanya gempa bumi, Yang ketiga adanya gelombang badai. Yang keempat adanya getaran. Dan yang kelima adanya peningkatan tekanan pada pori-pori. Likuifaksi oleh gempa bumi dapat dibagi menjadi dua, yaitu flow liquefaction and cyclic liquefaction. Flow liquefaction terjadi pada single sharing event atau di mana shear stress-nya lebih besar daripada kekuatan sebuah material atau bahan. Gempa bumi merupakan salah satu pemicu karena pemicu adanya flow liquefaction. Setelah terjadinya gempa bumi, maka kekuatan tanah akan rentan terhadap flow liquefaction. Karena tanah tidak lagi cukup untuk menahan tekanan statis yang bekerja pada tanah sebelum terjadinya gempa bumi. Dalam presentasi ini juga disebutkan bahwa likuifaksi akibat landslide atau tanah longsor terjadi dalam waktu yang singkat dan sangat berbahaya atau very dangerous hazard. Terus ya selanjutnya Miss Red juga menyampaikan bahwa tentang cyclic liquefaction yang terjadi akibat pembebanan cyclic yang terjadi pada endapan tanah dengan tegangan geser statik yang lebih rendah daripada kekuatan tanah. Deformasi akibat mobilitas cyclic berkembang secara bertahap karena tegangan statis dan dinamis yang ada selama gempa bumi itu terjadi. Tahapan cyclic liquefaction ini ada beberapa, antara lain yang pertama adalah hilangnya lapisan sedimen berporositas tinggi. Yang kedua adanya pemadatan sedimen selama terjadinya gempa bumi. Yang ketiga adanya tekanan pori-pori meningkat di mana efektif stresnya berkurang selama terjadinya gempa bumi tersebut. Yang keempat, adanya likuifaksi yang tertunda akibat pori-pori yang sudah kehilangan cairan itu kembali terdistribusi oleh cairan. Cyclic liquefaction ini dapat terjadi di area yang luas maupun yang dekat dengan permukaan. Sebagai contoh, gempa Niaga Jepang tahun 1964, di mana terjadinya likuifaksi yang merobohkan ke gedung-gedung di sana. Loma di USA, di mana likuifaksi terjadi di dekat permukaan, di mana gelombang gempa memicu litifikasi batu pasir. Hal yang dapat salah satu contoh flow likuifaksi adalah lateral spreading yang bisa terjadi di jalanan atau di jembatan. Berikut adalah beberapa contoh gempa yang memicu flow dan cyclic liquefaction. Antara lain ada di Wenjuan 2008, di mana terjadi landslide dan juga likuifaksi. Begitu juga dengan Padang tahun 2009, di mana cyclic liquefaction sangat merusak area tersebut. Dan di Kashmir 2005, di mana tanah longsor terjadi dan juga likuifaksi yang terjadi. Beberapa hal yang bisa dilakukan untuk liquefaction risk assessment antara lain adalah liquefaction susceptibility. Dalam hal ini adalah menampilkan pemetaan, di mana dalam pemetaan itu kita dapat mengambil sebuah kesimpulan area mana saja yang rawan akan likuifaksi. Yang kedua adalah liquefaction probability modeling, di mana kita dapat memprediksikan sebuah dampak dari sebuah likuifaksi. Jika terjadinya likuifaksi, mulai dari korban jiwa, berapa luas area yang terdampak, dan sebagainya. Serta kita juga dapat melakukan soil improvement method, di mana itu teknik-teknik engineering untuk membangun sebuah bangunan atau sebuah public area atau sebuah fasilitas atau infrastruktur, sehingga itu mengurangi dampak dari likuifaksi yang akan terjadi. Oke, sekian saja itu resume dari saya. Maybe we go to the discussion session, Ms. Reed. Hello?
Sorry, I was muted. Yes,
Okay.
please. Thank you.
Okay. Any question for the participant? Please. Okay. Mr. Bayu Pranata, time is yours.
Yeah, thank you, Miss Dr. Octavia. I will ask about the earthquake compare with the other earthquake in another country between Palu. If we compare, what which one is big massive liquefaction? What if we compare with the other earthquake, and how we know how we calculate big calculate with the how we calculate the measure of liquefaction? It's just casualties or the widespread or another? Can you?
So I think
About the question, Mr.
Ya, jadi gini, maksud saya tuh apabila dibandingkan dengan beberapa gempa lain, I'm sorry, in Indonesia, apabila dibandingkan dengan gempa-gempa yang lain yang mengakibatkan likuifaksi atau industri likuifaksi, saya lihat selain magnitude, parameter apa saja yang mengakibatkan likuifaksi itu lebih besar, dan ukuran likuifaksinya besar itu seperti apa? Tadi tidak dijelaskan juga di daerah lain itu seberapa besar sih likuifaksinya. Gitu. Jadi agak sulit kita mengukur atau membandingkan antara gempa-gempa lain dengan dampaknya gempa di Palu dengan dampaknya likuifaksi di Palu. Jadi itu saja. Terima kasih.
Okay. I will translate it. The first one and the first question is, what is the parameter about the liquefaction is bigger or what is the parameter you say the liquefaction is bigger or not?
I think, isn't it usually the number of square kilometers affected? If you have a liquefaction that's 10 square kilometers, that's more significant than 1 square kilometer. What would you say, Jessica?
What is the parameter? I think Ms. Bayu said that magnitude or anything else would be the...
Oh, do you mean like...
I'm sorry. And which one?
Go ahead.
Go ahead, Mr. Bayu.
Okay. And which one liquefaction is more, if we compare with other liquefaction, which one is bigger?
The difference between flow liquefaction and cyclic liquefaction in terms of the scale of the event. Maybe the flow liquefaction is really when it's often due to a landslide event. So the liquefaction might just occur in a small area, just the landslide, but that landslide mobility will be greatly increased by the mechanism of flow liquefaction. So it will spread very far. But you can have cyclic mobility or cyclic liquefaction kind of happening over a large area, but not destroying everything in that area, causing less damage over a longer or over a wider area, but it's still a lot of damage. I'm not sure if that answers the question.
Mr. Bayu, is it clear for your first question?
Yeah, yeah. I
The
mean,
first
like
question
we
is the
compare.
parameter, right?
Yeah, yeah. When we compare with the earthquake in Sichuan, how big liquefaction happened in there,
Yes.
and what the parameter? Yeah, if we compare.
So
I think they're trying to get a number, like earthquake has a magnitude 7.5. How about a number that's
Yeah.
associated with the liquefaction?
oh,
And how about the liquefaction? Yeah.
I would say that liquefaction can occur. That was a really remarkable event because the large magnitude earthquake caused a lot of landslides as well. But you can see cyclic liquefaction occurring in smaller earthquakes as well as kind of, and I would invite Dr. Mooney to contribute to that answer.
So I think, Jessica, the question is, if Wenchuan, what's the magnitude of the liquefaction for Wenchuan? Does it have a magnitude number, like liquefaction 5, liquefaction, like a hurricane? Hurricane is, you can have a hurricane 3, 4, 5.
Not to my knowledge.
No, no, it doesn't. She's right. The liquefaction people don't give a number. So the only thing they talk about is the total number of cubic kilometers of material affected. So we cannot tell you that the Kashmir liquefaction was a 7 and Wenchuan was an 8 and Padang was a 6. Maybe you have a very good idea. You should publish your idea in a journal and suggest a liquefaction scale. That would be we can call it the Pranata scale.
But
Good idea.
Yeah, you can capture my idea. It's okay.
Maybe I can help or answer the question.
Go ahead.
Okay. I have some research for some liquefaction event in Indonesia, more than 20 liquefaction, and I note the parameter liquefaction. The earthquake trigger liquefaction have earthquake low earthquake 0 until 70 kilometer and magnitude more than 6 and intensity more than 5 MME. And have focal mechanism dominated by strike slip, like that. The historical data from 37 even liquefaction in Indonesia from 1967 until 2080, like that. Thank you.
Yeah, and thank you very much. That's very useful. You cited the MMI value. You said greater than 5 and so on. Another value which is very commonly used is the peak ground velocity at the liquefaction site. So in other words, how much the ground is moving. And the peak ground velocity is usually greater than 20 centimeters per second. So there are ways to put a number on the triggering of the liquefaction, but I don't know of a number which tells you how big the liquefaction event is.
Okay, thanks for Mr. Mooney and Mr. Jimmy for the sharing. Any other question from the participant today?
Pep. Hello, Pep.
Hello. Okay. Mr. Eddie, time is yours.
Okay. Okay. Thank you. Hello, Jessica. I have some question for you. Is why does one of the parameter of the liquefaction risk assessment model, as described, use peak ground velocity input? And second one, can we identify the liquefaction of ground acceleration or PGA value from probability hazard mapping? Okay, that's the two questions from me. Thank you very much.
Okay, so that question is a very good one. You're asking for all of Indonesia, you have, of course, a national map which predicts the future probability of a certain level of peak ground acceleration. And yes, this kind of map is very useful if you combine it with the soil type map, because peak ground acceleration on hard rock will not cause any liquefaction or landslide. So you have to combine the geologic map or the near surface geology map together with the peak ground acceleration map. And you will find the curves that relate this in a publication by Idris and Boulanger. They have taken many examples. We can provide the reference later.
Okay, thank you very much.
Okay, I think the time is
Satu lagi nggak boleh, Mbak?
oh, boleh Pak.
Yeah, just excuse me. Just comment. May I give opinion? I think the secret liquefaction or flow liquefaction depend on the geometric form of the surface. If the geometry is slope, will generate the flow liquefaction. If the geometric is flat or circular sediment, will generate the cyclic liquefaction. It means that impossible flow liquefaction will occur in the flat surface. What is your comment? Thank you.
Go ahead, you can start, Jessica. I have an opinion.
Well, I think the question of the steepness of the slope and how that affects whether flow liquefaction will occur.
Right.
And flow liquefaction is really, I think it's a way of describing the mechanism, which is often triggered by a landslide. So if you have that landslide, maybe the landslide requires a steep slope, and then the liquefaction can really cause a flow that continues on flatter areas. But what do you think?
Well, I wanted to, you showed a photograph from Japan of some buildings which tilted over.
Right.
Turned sideways. What was the location and the earthquake for that?
That was the 1964
right.
Niigata event.
Right. So in 1964, Niigata was on a flat area, and the liquefaction was in the subsurface.
Right.
And the buildings tilted over, and there was a lot of damage to the living residences. It may be not deadly, but a lot of soil liquefaction in 1964 Niigata, and that was the beginning. That's when people began to put a very big emphasis on studying liquefaction. And that was a flat area. So it won't be flowing, but the buildings cannot stand. The buildings tilt over. Also dangerous and expensive. You have to remove all the buildings and replace everything. Very expensive. Thank you for your point and your comment.
Yeah, thank you.
Jessica, can we go to the Zoom chat? I will pick one question. Is it okay?
Okay, thank you.
Okay. From Nurul Hudayat, from Stagi of Kepahyang. His question is, will areas that are frequently shaken by earthquakes reduce the shear strength of the soil or become more susceptibility to liquefaction? Sorry, susceptible to liquefaction.
Maybe I can answer that one about whether earlier earthquakes will change the soil condition. Most early earthquakes will only be magnitude 4 and 5 and this kind of magnitude. And so they will not change the soil very much. The only way you can really change the soil characteristic is with a strong earthquake. And as you know, in the entire world, there are only 10 magnitude 7 earthquakes every year. So it's unlikely that the soil will have frequent large earthquakes. So I don't think it's a big factor, because most earthquakes, even in Indonesia, most of your earthquakes are magnitude 3, 4, 5, 5.5, 6. They will not change the soil much. Too weak.
One more question, Jessica.
Sure.
Okay, Mr. Jimmy.
Oh yeah,
Are you
thank
there?
you. Yeah,
Okay.
thank you very much for chance. Miss Jessica and Mr. Moni. One of recommended geological method to research related liquefaction is trenching. But I had attend some seminar and about liquefaction. There's no can give me sharing knowledge about determine correct trenching location. May you help me to sharing maybe your scientific opinion about the determine correct trenching location to research about liquefaction. Thank you.
Yeah, so Jessica, the question is where should people trench in order to gain knowledge about the susceptibility of a region to liquefaction? What do you think?
I don't know. I think the geotechnical engineering would have some good guidance on that.
Yeah, so what we do at USGS is first we go to the study area and we use shallow seismic, MASW, multi-channel array seismic analysis. And we look for the area that has thick sediments with low velocity. Then we communicate to the geologist who will do the trenching that location is quite suitable because it has low S-wave velocity and very thick sediments. So then they will choose that place. Thank you.
Okay, thank you, Mr. Moon.
Okay, I'm sorry for the participant because the time limitation. I think you can use the Zoom chat to another question for Jessica. I will pass it to her after this session. Thank you, Jessica, for your presentation today.
Thank you very much.
I hope you have a nice day after that. So we go to the next session. The presenter will be Mrs. Estenwood. Good morning.
Hello. I am ready when you are. Yes. I am ready to get started.
Okay. Mrs. Estenwood, she studied geology and planetary science at Florida Atlantic University. She works at USGS as a geologist from 2020. Now she will present about hazard mitigation. So, Mrs. Wood, time is yours.
Thank you so very much. Let's get started on our final presentation for the lecture training. So let me share my screen. Oh, my apologies.
Yes.
My apologies. All my emails. My computer has a mind of its own tonight. So lecture 21 on natural hazard mitigation techniques. There are some supplemental videos in the recorded version of this lecture, so feel free to review them after today's training. So hazard mitigation is the implementation phase during disaster management tactics and policies, as well as disaster management practices. But in order to really understand what natural hazard mitigation is and how it differs from natural disasters and disaster mitigation, we have to understand that disasters are only disasters when there's an at-risk population being affected by the natural hazard. Natural hazards can occur everywhere, and so only when it's exposed, these hazards are exposing potential damage and loss of life to different population sizes of either 100 of individuals to several million. That's when it's considered a natural disaster. We're able to look into how to properly mitigate by analyzing risk. Risk takes into the consideration of community exposure, the natural hazards that are present within the area, and the vulnerability of that community to the hazards. We're able to evaluate risk through several different methods. One is through community awareness surveys. This is when we engage the public by performing surveys in areas where there's high vulnerability to certain disaster types and hazard types. And we assess whether they have the knowledge that these hazards are present within their given environment, and if they know how to properly evacuate during natural disaster warnings and declarations. We can also do this through community needs assessments. Community needs assessments are slightly different from community awareness surveys, as community needs assessments are normally done on a government to public sector level within agencies. Emergency planners normally are responsible for doing community needs assessments. They determine the budget on how much funding can go towards disaster mitigation for certain geographic areas, as well as for certain cities based off of population density, and also which areas need updating, such as perhaps a city doesn't have as many evacuation zones as it's required based off of new policy changes. And so that's what the community needs assessment goes into and addresses. And also investigates deeper into vulnerability of an area. We're able to determine vulnerability by looking into the density of population. Here we have a diagram that goes into vulnerable population and the amount of funding that each population gets. For the urban high income insured and quality of housing, their vulnerability is relatively low, but they get much more disaster funding than, say, more indigenous neighborhoods due to lack of communication with those with that demographic. And so indigenous neighborhoods have extreme vulnerability and decreased funding because nobody's really doing site investigations or willing to communicate with those individuals. And that creates a problem in the future for those people within that given demographic. Site investigations looks into how we identify where the hazards are in relation to a city or regional area where people are at risk or vulnerable to disaster types occurring. We have a diagram on the right-hand side that kind of goes into several different types of hazards that are present or that are occurring based off of either anthropogenic consequence or just happening normally within the given environment. We are able to do a site investigation through compaction reports, proctor testing, soil boring, and looking into how much water withdrawal has been occurring in underground aquifers and from the groundwater table. This also deals with well site inspections, whether it's for water or oil related purposes. We are also able to use natural archives as a way of doing hazard mitigation. Natural archives can be anything from personal journals that were keeping record of a possible earthquake or hurricane or tsunami that originated back in history, or it can be something more extreme as the image shows here on the right-hand side. This is actually a picture of the Nojima Fault. It's in a museum in Kobe, Japan. This is the fault that was responsible for the Tohoku earthquake that happened, where it was, I believe the magnitude was almost up to 7 for the Tohoku earthquake in this region. They actually built a room around the Nojima Fault that was exposed and dug out some of the sediment in that area, so that way they could put on display how this fault was responsible for the Tohoku earthquake. So this is a perfect example of a natural archive in a museum, and also a very extreme example. Tribal oral traditions can also be used for natural archives as well. We also go into early warning systems. These can either be international or regional based. Early warning centers on an international level require international collaboration in order to be successful. Without international collaboration, this can provide inaccuracies in data and prediction of potential disasters that are going to impact the regions of being affected. So we see this with the tsunami early warning systems, how there are several different issues that can arise should, say, the early warning detection center in Hawaii is showing conflicting data to that of the same or a similar tsunami early warning center up in Alaska. Dealing with regional early warning centers, we have just basic remote sensing devices that use geospatial satellites in order to measure and record changes within the given environment. These readings are then passed along to the communication satellite. The communication satellite is able to take all the information to the emergency planners, so that way the emergency planners can assess what changes are occurring from these sensors out in the environment. It's good for detecting seismic events, as well as the possibility of wave generation depending on where the sensors are located. And this can allow for emergency planners to decide if an area needs to be under evacuation warning or not. We can also go even further with this in geospatial involvement with GIS predictions and GIS mapping. We can look into data provided by the GRACE satellites, MODIS, and the Pleiades satellites to determine if there's any surface level changes or subsurface level changes that are occurring that we can see from satellite imagery that can then be used later to assess whether or not that area should be investigated further for potential disaster to occur. And we can even take GIS technology and apply it to AI and mobile app utilization. So that way we can have real-time disaster mapping capabilities, such as the Shake Map or Did You Feel It applications that we have with the USGS. Now I want to go into a flood-related disaster that happened in Sagira in the Banten province on the western coastline of Java. This happened at the beginning of the year during the heavy flood incidents that happened in January of 2020. Here we see Sagira showing the houses are very close to one another. The neighborhoods are very consolidated. There's also areas along the riverfront where there is agricultural land, and then there's very few natural barriers separating the agricultural lands and the densely populated areas from river exposure during floodplain. And then we can also see here that there's a little bit more protection from potential floodwaters between this densely populated area and the forest that's happening here. However, following the flood potential and the flood disasters that occurred at the beginning of January 2020, we see the same river has caused the floodway fringe to expand outward because the water had nowhere to go. There was no proper outlet for some of the heavy rainfall flooding to empty out. And so here we see, I translated the legend on the side, but I have it in both its original format and in English. And we're able to see that the yellow section is where a bridge has been knocked out due to the floodwaters, which means that emergency service providers were unable to get to some of the people here after the initial flood event. And then we also see these blue stars, and the blue stars are representative of areas where the particular field researchers actually surveyed to see which homes had been affected during the actual flood event. However, I'd like to point out that that area down here, where there was some additional protection, has actually undergone a mud flow. A mud flow has occurred and actually just wiped out all of the natural barriers that were existing here from the trees and everything. And so these houses ended up also experiencing flooding damage, even though they should have had much more protection than some of the other homes. It's great to know this information, to be able to see it with the satellite images and then to be able to track it. But unless we are able to zone these areas, we can't properly mitigate against them. In order to prevent things like this from happening in the future, within the United States, we have the Federal Emergency Management Agency that uses the National Flood Insurance Program to create floodway maps. So this one is an example of a flood map for Broward County in Florida in the United States. Here we can see, very similar to Sajira, there's some densely populated neighborhoods and potential areas for extreme flooding from man-made channels and different river networks that are going through. And Broward County has taken the initiative to do this with that same map, where they have designated different zones based off of color on which areas and which neighborhoods are more susceptible to flood-related damages. We see this further by looking at the actual legend that accompanies this map. These areas in blue are zones A through V, and they have the highest potential for extreme flood related damage. And the orange areas are a 1% chance or within the 100-year floodplain of suffering similar damage to the green and blue areas. For the gray areas, or the areas that are not colored, these are areas that were not assessed during the initial flood map, and so they must be observed later on in order to add to this map and create more accuracies with it. By creating these zones and identifying which areas they are, we're able to figure out which parts of the neighborhood need to be immediately evacuated following heavy rainfall potential, as well as whenever coastal flooding occurs.
Berangkat satu tim dulu sih, Mbak.
It is all good. We will continue. But yes, so we are reviewing information based off of prior data with flood maps, and then updated data with flood maps following new site inspection policies in order to understand how to properly implement mitigation strategies. So something like what would happen normally or what happened in Sajira won't happen again. And so that's why it would be a good idea to implement flood maps, especially around coastal regions or areas where rivers are located near heavily consolidated neighborhoods. So that way emergency planners and disaster managers are able to properly help implement mitigation tactics that are successful in those areas that prevent, well, not prevent, but reduce the amount of damage and loss of life that can happen following a flood event. This goes into my next point, that communication is very much the most important part of hazard mitigation. We need collaboration in order to have successful hazard mitigation techniques. Without collaboration between government and public sectors, as well as with government, national, and international agencies, we're not able to innovate further mitigation tactics that could be better implemented in areas where disaster frequency and more disaster prone areas are. So the more communication that we involve that engages both international and community involvement, the better the potential that disaster resiliency can finally be achieved in a given area. Looking into global initiatives, there's the Sendai Framework, as well as the Sustainable Developmental Goals with the Paris Climate Agreement. I went into the Sendai Framework particularly because of their disaster risk reduction program for 2015 to 2030. Sendai Framework may be something that's very familiar for Indonesia, as Indonesia does participate in the Sendai Framework. It covers the disaster risk reduction by looking into substantially reducing global disaster mortality, the affected population, and number of affected population, looking into how much economic loss occurs during a disaster versus the global GDP, and reducing the disaster damage to infrastructure that's being implemented. And they do this by substantially increasing the number of countries involved in the Sendai Framework that follow the disaster risk strategies, as well as looking into the enhancement of international cooperation to developing countries and the availability and access to multi-hazard early warning systems and disaster risk reduction assessments. And so again, the majority of what the Sendai Framework is suggesting is substantially increased communication while substantially reducing loss of life and damage to property. One of the ways that they do this is through a collaborative simulation with the United Nations Disaster Risk Reduction Office. This is called Stop Disaster. It's actually a video game simulation. They're becoming more popular in disaster management and public health industries, and getting the public engaged in understanding what potential risks disasters can present to a given area. And so we look at a scenario that was run through. I had done this scenario and copied the disaster mission report to follow. This one was following a tsunami related simulation. The information in Stop Disaster actually utilizes real world information. And so what your role is in the simulation is to act as the disaster manager and to place mitigation techniques such as slope stability poles, as well as the building of hospitals and emergency evacuation centers. So that way you can reduce the vulnerability to potential disasters being run during the simulation. So for the tsunami one, I put one school in an area that was very much not well protected against from floodwaters. And I built a hospital up on a higher level area with the proper earthen levees. And in the mission report, it shows that the school was destroyed because of the area that I chose, which was a lowland near coastal zone area. But the hospital was able to exist. However, because I built a levee in front of the hospital, it caused more significant damage to the houses nearby, which we see in the total damages column, which is up to 10,000 USD. And it also shows that 32 buildings were destroyed because I chose to build the levees around the hospital and didn't take time to actually build up the levees near the houses as well. That's what's great about these simulations, because you can choose which one you want: tsunami, hurricane, wildfire, earthquake, or flood related events. And it gives you a score that tells you whether or not you successfully achieved disaster resiliency, or if you need to work further on building up disaster resiliency during that simulation procedure. Then we have the Sustainable Developmental Goals of 2030 in accordance with the Paris Climate Agreement, dealing with disaster risk reduction and disaster resiliency. There are actually 6 that do this. This is the clean water and sanitation goal, industry, innovation, infrastructure, climate action, affordable and clean energy, sustainable cities and communities, and life on land. I would suggest that following this training, that investigation into these 6 SDGs for 2030 should be reviewed. So that way you can build a better understanding of what each of these do in relation to reducing vulnerability to disaster prone areas. It's extremely insightful. Now I'm going to go into some short-term solutions versus long-term solutions with hazard mitigation. So for short-term solutions, we have dams, levees, and seawalls. Here on the right-hand side, we have an example of a failed earthen levee. And as we can see, the cars are unable to get across the levee now because it has failed in this area. This is actually a levee in Texas in the United States. Levees can fail for a number of reasons. Floodwaters can get too high. There could be erosional forces at play. Earthquake potential can also damage levees. But for this particular incident, what happened was seepage occurred. And seepage is actually one of the contributing reasons to earthen levee and dam failures. It's when the soil moisture, the infiltration rate after heavy rainfall or flood-related events ends up saturating the soil so much that it actually pushes the water up and under the dam or the levee up into the other side until to the point that the pore space is so separated that it acts very much like liquefaction, or I guess you could even say quicksand. And what it does is it actually causes the water to create dam and levee failure on the opposite side of the dam or the levee and causes the structure to ultimately fail. This is one of the reasons why it's considered a short-term solution. Another reason for short-term solution for dams and levees and seawalls is that it actually pushes floodwaters and tsunami waters to other areas that are not protected. So if you have a higher levee in one area compared to another levee in a different area along a coastal region, and there are some high tide waves that are coming in that could cause coastal flooding, can actually push the higher levee will actually cause the waters to travel around it and will actually flood the area that has lower levees because it now has a higher wave potential than where the higher levees were. Another short-term solution that we can look into is building codes. Building codes are great, but they constantly require updates, and you cannot use a one-fits-all scenario for building codes. Here I have a simulation. It's very quick and it doesn't require sound. It just requires some quick explanation. This was done in an earthquake simulation laboratory in Japan. And what it is it's showing building A, which is here on the left-hand side, and building B on the right. They both have the exact same building codes in place. However, building B has more protection and the ground beneath it has more stabilization in this scenario than building A. And we can see that by these beams here for building B that don't really have the same position as building A. So the beams are running horizontally for building B and the beams are running vertically for building A. And this is supposed to simulate different stresses from different types of faults that each home could possibly be built on. So now let me play the simulation and we can show how similar building codes with different ground stabilization can result in different effects. And again, there's no sound for this video, it's just purely observing. But they'll experience the exact same magnitude of seismic activity. And we'll get to see the results. This is what makes this so interesting, because building A has completely been devastated with the same seismic activity and the exact same building codes, but because it had a different stabilization for the ground and for the foundation, it wasn't able to withstand the seismic event so much as building B could. So now we go into long-term solutions. Long-term solutions include community training, which is actually what we're doing right at this moment when government and international agencies get together, create specified and authorized lecture material and teach it to professionals and students, so that way they can take that same information and apply it in their everyday lives and their work lives to better improve the community that surrounds them on disaster resiliency techniques. Another long-term solution is green city planning. Here I have a diagram with some ecological and sustainable city planning ideas that have been suggested by the United Nations as methods of reducing damages following seismic and flood-related disasters. One of the big ones is urban distancing, building the homes away from one another, so that way if one building is damaged, you cannot possibly damage the building right next to it. I also put this building next to a river, showing that an enhanced bankment or following river revetment procedures can help reduce the flood fringe, so that way the flood waters don't actually move up into the floodway. They're able to be channeled out into different areas. And then we have foundation stabilizers. Foundation stabilizers can be anything from slope wedges to different types of poles that can go further into the ground. There are some foundation stabilizers being experimented with dealing with liquefaction and landslide potential. So that way, instead of the home being affected by the liquefaction event, instead it simply moves with the sediment as the sediment is moving. So it doesn't actually sink. And they're doing that with poles underneath the foundations. So that's something really exciting that they're considering looking into. More research is needed for that, but that is one direction that they're going. And then there's also the involvement of aquaculture, or creating man-made wetlands. And this can help during landslide and flood-related disasters, because it allows the wetlands to act as a natural barrier to prevent sediment from being transferred and lost around where the urbanized areas are. And so this is some good examples as provided by UN examples of different types of green city planning. And then debris management. Debris management is, I believe, the most important long-term solution for hazard mitigation techniques. Debris can be as simple as plastic trash to broken buildings and fallen tree limbs and different types of it can even be as something as significant as a car washed away during a flood event or during tsunamis. When we do proper debris management, the removal of these debris into designated areas as designed by disaster managers and planners, we're able to reduce the cost of potential damage that will follow, as well as allow for emergency service providers to reach areas that have already suffered the disaster, so that way they are able to properly evacuate and provide aid to individuals that normally wouldn't have been able to do if there had been a debris barrier that had emerged. So in the event of flooding, say we take example of flood-related event where a house has been swept away in the flood and is now considered debris. If that damage from that house has not been removed, it can actually cause debris barriers to form in that area. And so following the next flood event, it could actually cause floodwaters to rise up because it has even less of an outlet to escape from. And essentially the debris barrier becomes a debris dam. And so it causes even more significant flooding within that particular area. I have a small diagram on the right-hand side that also shows this. It shows in the red lines that the floodplain extends only to the red lines. However, there are fallen tree limbs, trash from the last flood-related disaster that happened that have not been cleaned up by disaster planners and people within the community. And so the flood fringe has now extended from the red lines to the black lines because the water is now being essentially dammed by the debris dam. And so now the floodplain has extended outward and is now more capable of affecting homes that were not currently built within the existing floodplain, but now exist in this particular flood fringe zone. This is why it's so important to go into into debris removal for disaster mitigation purposes. And obviously, the healthier your environment following a disaster or following, it doesn't even have to be a disaster now that I think about it. It could be as simple as normal pollution. If you know that there are things that cannot be biodegraded, it's going to eventually cause a debris barrier to form if it's not properly handled through debris management. So the healthier your environment, the more disaster resiliency you can build. This is something that's stressed significantly with many other global initiatives, especially in the Ramsar Convention on Wetlands, which believes that the more protection that we provide for wetlands, the more disaster resiliency an area is able to acquire, and the more pollutants are able to be absorbed out of the water that also help to diminish the emergence of different public health related problems that people can experience. And ultimately, I keep saying the word disaster resiliency. Disaster resiliency is a cycle of different techniques and different tactics that make up the foundation of hazard mitigation. It is the development of sustainable and resilient urbanization and infrastructure, the prevention of debris, and the prevention of introducing new pollutants and possible other impacts that can contribute to the intensity of a given disaster, the reduction process, which goes into the reduction of damages, cost, and loss of life, and then the recovery effort, which is going into reassessing and updating current mitigation strategies so that way this cycle can continue and disaster resiliency can continue to rise further up. And this is achieved again through government, public, private, international, and community involvement, and must always consider all possible interferences within the environment as well as anthropogenic consequences to help build this disaster resiliency in the future. And that concludes this presentation.
Thank you, Mrs. Woods, for your nice presentation today. I would like to summarize your presentation in Bahasa.
Yes, of course.
Okay. Presentasi Mrs. Aston Woods pada hari ini mengenai teknik mitigasi kebencanaan. Dalam hazard mitigation diperlukan untuk mengetahui beberapa hal, yaitu pertama adalah analisa resiko, yang kedua adalah sosialisasi, di mana penduduk harusnya mengerti dan agar lebih mengerti dan waspada terhadap adanya bencana. Yang ketiga, mengetahui tentang kebutuhan penduduk sekitar, di mana pemerintah harus menyediakan berapa besar dana yang diperlukan untuk mitigasi bencana, menyediakan zona evakuasi, dan juga menyediakan fasilitas rumah sakit di sekitar daerah bencana. Yang keempat adalah diperlukannya lokasi penelitian, di mana kita harus meneliti dilakukan survei di area yang beresiko untuk mempermudah penduduk dan pemerintah dalam mengatasi dampak dari sebuah bencana yang akan terjadi. Yang kelima adalah mengetahui catatan kejadian kebencanaan setempat atau historinya. Untuk hazard mitigation ini sangat diperlukan pusat peringatan dini untuk mengatasi dampak dari bencana tersebut, di mana kerjasama internasional dan nasional akan mempermudah proses mitigasi jika bencana terjadi. Kita dapat melakukan prediksi melalui teknologi GIS, di mana teknologi GIS ini mempermudah dengan menghasilkan disaster mapping, di mana pemetaan kebencanaan melalui satelit, contohnya di Sajira Indonesia pada tahun 2020, di mana daerah tersebut dilihat dari satelit mengalami dampak banjir bandang baik sebelum maupun sesudah kejadian banjir pada tahun 2020. Berapa jumlah bangunan, jembatan, dan juga rumah yang terdampak akibat banjir tersebut. Hal ini dapat dilihat dari disaster mapping melalui teknologi GIS. Yang kedua, kita juga dapat melakukan pemetaan bencana seperti flood map, di mana pemetaan ini dapat mempermudah untuk melihat area mana yang akan terdampak oleh bencana banjir untuk mempermudah mitigasi bencana. Salah satu hasil inisiatif global dalam mitigasi bencana adalah Sendai Framework, di mana Sendai Framework ini bertujuan untuk pertama adalah mengurangi jumlah korban jiwa, yang kedua mengurangi jumlah korban yang terdampak, yang ketiga adalah mengurangi jumlah dampak ekonomi setelah terjadinya bencana, yang keempat mengurangi kerusakan infrastruktur, yang kelima adalah meningkatkan strategi pengurangan risiko bencana. Yang keenam adalah meningkatkan kerjasama internasional dengan negara-negara berkembang lainnya. Yang ketujuh adalah mempermudah akses multi hazard untuk early warning system dalam pengurangan risiko kebencanaan. Dalam presentasi Mrs. Woods tadi dapat disimpulkan solusi sementara untuk mengurangi risiko kebencanaan, yaitu pertama adalah membangun dam atau bendungan, tanggul, dan juga sea walls untuk mengurangi risiko tsunami maupun likuifaksi. Yang kedua adalah melakukan building codes, di mana teknik pembangunan ini sangat berpengaruh terhadap ketahanan bangunan dari sebuah bencana. Contohnya adalah dari bencana gempa bumi. Yang ketiga adalah melakukan green city planning, atau di mana suatu bangunan lain, satu dan lainnya itu memiliki jarak tertentu. Kemudian bangunan tersebut memiliki foundation stabilizer untuk mengatasi dampak dari likuifaksi yang mungkin akan terjadi, serta aquaculture untuk menampung air. Yang kelima adalah debris management. Hal ini dilakukan untuk mempercepat mitigasi saat terjadinya bencana banjir. Sekian. Oh iya, satu lagi. Ketahanan bencana ini terbagi menjadi 4 faktor, di mana yang pertama adalah urbanisasi, yang kedua adalah recovery, yang ketiga adalah reduction, yang keempat ada prevention. Sekian summary dari presentasi kali ini. Mrs. Wood, we go to the discussion session.
Yes, can you hear me?
Yes, I can hear you.
Okay, my screen, my whole computer just froze. And so I was very worried that my sound wasn't transferring through. I don't know what's happening with my computer, but I can answer questions. And then I might need to log off after questions and log back on to the chat.
Okay,
Yes.
okay. So for the participant, you have any question for Mrs. Woods? Please raise your hand. Oh, I think there is no question directly for you. I will take from a Zoom chat. Is it okay?
Yes, that's perfect.
Okay. From read one, PGT. Most of the information dissemination in Indonesia use internet communication. When during the big earthquake, the communication was also disrupted. What do you think about the solution of to these problems?
Okay, so this is actually something that this is a really great question. I spent some time in Japan trying to figure out this exact solution during a research project where I was out in the field with several other researchers and geologists, and public health and disaster managers, who were trying to understand different types of mitigation tactics and techniques. And while we were in Japan, we noticed that what they did in lieu of disruption of communication, particularly dealing with internet communication, what they did is they had designated areas all throughout their city where they had emergency evacuation guidelines. And they also had something very simple. A they had several different vending machines along the way. And what you could do is they had an emergency kit on the inside of each vending machine. And so the vending machines would unlock following seismic activity. It had a pressure plate on the inside, so you didn't have to worry about it during electrical failure. And what happened was you were able to access the emergency kit within the vending machine, and it had a radio receiver that could connect directly to radio broadcast of evacuation procedures should the internet have gone out. And that was something that we found extremely exciting when we were looking into hazard mitigation tactics and how to um, utilize those same tactics here in America. I would definitely say that would be one way to possibly bypass um, a internet failure and cell phone tower failure during a disaster related event. Another thing that we also noticed while we were in Japan, me and my research team, was we noticed that again they had thicker guidelines, but they also had these artificial hills that they had created. They had filled the hills over with shotcrete. And what they had done is they had created these wedge platforms. So during shaking events, people knew to go to these shotcrete areas with these wedges and just wait on top of them because they were separated away from buildings, different types of potential debris, such as like falling tree limbs and uh, falling rocks and everything like that. And so that was also something that we ended up bringing back to America as a suggestion for earthquake mitigation. Whenever you can't get a hold of anyone over internet and communication, is making sure that your community is aware of proper evacuation zones. So I would say those would be the most successful from personal experience.
Okay, thank you for sharing, Mrs. Woods. Any other question? One more question, I think. No question, I think.
Yeah.
So I will check from the Zoom chat. Only one question again. One of from Angga Research and Development Center.
Mhm.
One of the challenges, in my opinion, is increasing the awareness of the common people about the potential for a disaster and how the preparation and response that needs to be done to deal with it. What your recommendation and opinions regarding concentrate and practical steps for mitigation in Indonesia, which have the potential to occur with very complex natural disaster like tsunami, liquefaction, volcanoes, flood, and even climate change are the specific scientific studies that you think we BMKG really needs to do?
Okay. So I will answer the specific study one or the discussion questions that could be posted on the discussion chat. For this one, for engaging the public during mitigation strategies,
Yes.
the best way to do that would be to implement educational programs, starting with primary and secondary level education, showing them the proper methods of cleaning up debris after a disaster. And it could be simple things as like just picking up twigs or collecting plastic trash or large tires, things like that around their area that could contribute to debris dams and debris barriers during disasters, and also helping them to understand where the evacuation zones are, understanding the mechanisms behind why damage occurs because of these disasters. And then as you build up this educational awareness on a primary and secondary school level, you're able to then engage the public not only through the students, but also through the parents of those students who are then able to collaborate with their children into learning what potential mitigation processes are being implemented in their community. I would also say that the best way to do this as well is making sure that if you're working for a government agency and you want to engage the public so that they know what you're doing as far as hazard mitigation implementations and policy changes, to make this public information. So making it available on the internet, posting it in media sites such as social media or even newspaper, and having different types of lectures, possibly going into these primary and secondary schools to actually lecture about, look, we have this new policy in place. Maybe you can teach this to your students and your students can take this information to their parents so that way they know. This is a common practice that we use here in America in order to get people engaged in understanding what types of hazards are present in their given community. And this was also true again in what we experienced, me and my team of researchers, what we experienced in Japan was education. Disaster education started fairly young. It also started in the elementary school level and was transitioned all the way up into university level. So I think that would be a really good strategy to implement that Indonesia could consider if it doesn't already have that availability for mitigation tactics and engaging the public.
Okay, thanks for your answer about Mr. Angga question. I think the time is up today. Thank you. Thank you, Mrs. Woods, for your presentation today.
Thank you, everyone. And I am going to log off and then try to log back onto the Zoom meeting because, like I said, my screen's still very much frozen. So.
Okay. Okay, thank you, Miss Jessica, for your presentation today. Thank you, Walter. Okay, so we go to the next in this course, Mbak Dona.
Yeah, thank you very much. Thank you very much for Miss Nur Octavia and Miss Audia Kaluku, and thank you very much, Walter. And I would Miss Wood and Miss Jessica Reed, and thank you very much for your great presentation. So maybe I have attended. I have attended a guest of this closing ceremonial, and we have attended to staff of Professor Dwi Korita. So welcome to maybe give me one sorry, yeah, give me 1 minute. I want to coordinate with our team.
Ladies and gentlemen, also distinguished participant, we would like to ask your patient for to be waiting for a couple minutes. We need to condition to coordinate with the Secretariat Office of the DJ, and thank you for your patience.
Pesertanya geofisika, ada UTT, ada balai, 55 orang.
Welcome to Professor Dwi Korita Karnawati. Thank you for attending.
Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh.
Yang ini kenapa? Silakan, Mbak. Hello,
Yes, Ibu.
Mr. Muni. Hello, Dr. Walter Muni. Thank you.
Good
Dan
morning.
ini
Good
juga,
morning.
ya, good morning. Oh, still morning. You are still in US?
Yeah, California.
Oh, in California. Good morning, ya.
Yes, thank
Okay.
you.
Thank you very much for your support.
You're welcome.
Please, yeah, thank you. Mbak, silakan, Mbak.
Mbak Audi, dipersilakan Mbak Audi.
Baik, Ibu, terima kasih. Mohon izin. Kita akan segera memulai acara penutupan pada siang hari ini. Your Excellency, Director General of BMKG, Professor Dwi Korita Karnawati, MSc, PhD, the Honorable Deputy Director General for Geophysics, Dr. Insinyur Muhammad Sadli, Master of Engineering, the Honorable Mr. Walter Muni from Earthquake Science Center, United States Geological Survey, the Honorable all Director for BMKG and USGS College, trainer, instructors, and facilitators, participants, distinguished ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Welcome to the closing ceremony for Advanced Earthquake and Tsunami Hazard Training Course. First of all, let us say thanks to Allah Subhanahu wa Ta'ala, who has been giving us mercy, guidance, happiness, and healthy, so we can attend and participate in this event. Ladies and gentlemen, the first agenda, impressions and message from the training participants, will be represented by Mr. Jambari from Angkasa Geophysical Station, Jayapura. To Mr. Jambari, time is yours.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Is my voice clear?
Yes.
Okay. Well, I'm feeling a little bit nervous. You know, I've never understood how I'm imagining standing in front of you directly, not in this virtual platform. Okay. Good afternoon, ladies and gentlemen. On behalf of this class, Advanced Earthquake and Tsunami Hazard Training Course, I would like to thank to all the people who make this training excellent. To the staffs who work tirelessly coordinating everything to make this happen, we thank you. To the lecturers for all your passion, wisdom, and knowledge you shared, we thank you. And to all the participants for all your attention toward the lecturers, even though sometimes you didn't understand what the speaker was talking because it's too fast for non-native, we thank you. And today is an exciting day. Today, I'm going to give you a speech. Now, graduate. And I want to give a big congratulations to everyone, including myself, for being here. The world we live in is plagued with dangers: earthquake, tsunami, climate change, COVID-19, time zone difference, and facial acne. Despite all the odds, we still managed to graduate. So let's give us a big round of applause. I don't know if you know me, but I'm Jambari. My friends call me James. My friends call me Lucas. Also, my friends call me James Berry. I'm going to tell you a little bit of my background. I'm living in Jayapura right now, but my hometown is Merauke. When I was in junior high school, my first encounter with earthquake and tsunami was the December 26th Aceh tsunami. Since that, I wondered why there are no earthquake in my town. But I know now, because it's Australian craton, but with LO 2012. Or Miss Hallie Puchara would say, it's a fragment of a continent. Long story short, I'm working for BMKG in Geophysics Station in Jayapura now. I'm wondered why there are no volcanic arcs in northern Papua. And guess what? Now I know. Mr. Walter said, it's because the depth of the subduction is not deep enough for magma to come out to form a volcanic arch, perhaps in the future. Well, I'm living in Papua, a province in eastern Indonesia with the lowest human development index in Indonesia. My day-to-day routine in the office is localizing or analyzing earthquake signal, but somehow I'm feeling pity. The main task is to analyze earthquake below magnitude 5, but the number of phases or stations that recorded are not sufficient. And then size completely said, error, cannot locate. But my head would say, thank God, you got me work easier. All in all, Papua is beauty and unique. Unique with its bird head fault complexity. When I'm working, I'm always worried if earthquake and landslide tsunami-genic occurred in northern Papua or other trains because we do not have proper warning system, especially for the coastal community. I used to visit USGS website, earthquake.usgs.gov. It's amazing website. I'm amazed by how massive data and the publications are. How could you guys maintain such a huge system? How on earth you have the earthquake data from whole the world? And talking from the student point of view, are all those data in archive already in measurement magnitude? Question mark. Anyway, your works are always impersonal. That is why I'm proud to be part of this training, being taught directly from the expert. So Mr. Walter Mooney, Sean Hatching, Hallie Puchara, Jessica Reid, Marcela Cilia, Aston Wood, Carol Barrera, Daniel Munoz, and Harrison Tunnel. One more time, thank you. And I got a special message for Mr. Walter. We're okay. We're fine with slow or fast speakers. We're okay with endless flood of English words. So I wish this kind of training will always be held each year. In conclusion, this has been one of the hundreds of life lessons I have learned. Thank you to teach each of us lessons. If there's anything you take from today, remember that to leave a legacy and to achieve greatness is not to get money and recognition. It's to leave those with whom you cross paths with a little more happiness and hope. Our time here together will not be remembered by grades, but by our relationships. The kind of person you are. These are the legacies, the kind of we must leave. Advanced Earthquake Tsunami Training Course 2020. It's been amazing 5 days with you. From the bottom of my heart, I wish you a very, very, very best. Thank you.
Thank you, James.
Thank you, Mr. Jambari, for the impressions and message representing the participants. The second, impression and message from the trainers and instructors will be represented by Mr. Walter Mooney from Earthquake Science Center, United States Geological Survey. To the Honorable Mr. Walter Mooney, for this time is yours.
Thank you so much. Once again, I would like to thank everyone who has participated and worked so hard to make this course a success. I appreciate your engagement and your enthusiasm. For everyone from USGS, this has been a really memorable experience we will not forget. The key concept behind every lecture that you have heard has to do with high quality data. Without these measurements coming from satellites or on the ground or in the ocean, we cannot understand scientific problems and make progress. Following on this thought, it's clear that future progress in earthquake and tsunami hazards in Indonesia, as well as all your other natural hazards, depends on your continued and expanded collection of scientific measurements. For example, the big expansion of your seismic network is a very important step in the right direction. It has been a goal of this course to introduce modern data analysis methods as well. For example, we discussed finite earthquake fault models, earthquake focal mechanisms, three-dimensional views of the seismicity, computer models for gravity and landslide and tsunamis, and even the use of advanced satellite data like synthetic aperture radar, so-called INSAR measurements. So good data and good data processing. I've been working with BMKG for about 20 years, and I can see that the greatest strength is your professional staff. USGS knows that your staff is very competent, well-educated, and motivated. However, everyone needs to renew their knowledge and expand the depth of their expertise. So these kind of courses are very valuable for both sides to make progress on advancement. So thank you all. It's been a wonderful experience. We do it all now with a computer with pictures of each other. It used to be we got together. I hope we will get together in the future. Thank you, and see you soon.
Thank you, Mr. Walter Muni, for your speech. Ladies and gentlemen, we are now going to the next agenda. Summary report from organizing committee will be delivered by Head of Research and Development Center for BMKG. To the Honorable Mrs. Nelly Floridariama, time is yours.
Thank you, Audia. Finally, we are in the last session of our training course. I would like to say maybe right now it's still good morning or late evening for our US colleagues. I also want to thank for Professor Dwi Korita, our head of BMKG, for being able with us today to give the closing speech, and also for Dr. Sadli and all the directors in BMKG. I want to share my screen. Madonna, please help me. Okay, on the next, I want to thank to all the trainers, Walter, Son, Carson, next, Hall, Jessica, Marcella, Aston Woods, Carol, and Daniela. And you can see that 66.67% are female. So it's very, very interesting. And of course, thank you very much for all the preparation that you have been made. We know that, of course, behind all the presentation, that I believe that you have done many works to prepare that and sharing to us, including how you record all the files of the presentation. So we have the video recorded before we enter the class. I think it's really, for us, it's very, very honor to have you here to give the presentation. And for me, myself, I just am amazed how USGS do research on our region with your data, and I I also agree with Walter that if BMKG data can be added to this research, I think maybe it will drive us for the new invention on earthquake science. I do believe on that. And I also thank you and notice from the discussion that we have during the last 5 days that many ideas are coming out from and give us idea how we will continue with our next research project that may we establish for our next collaboration with USGS. Next. I also want to thank you for all participants for your enthusiasm and how you contribute through the question and sharing knowledge, especially how you can give us on your local condition. I think this kind of discussion will give also the USGS College get better understanding on our region. Next, you can see the graphics here. Only 21% are female. I hope that maybe on the next training session we can increase the female participation. Next, and we have do analyze of the words that come up frequently during our lectures, and you can see that liquefaction is the number one that always the number one word that we frequently use in these lectures. I think it's related to the Palu liquefaction that happened just in the recent time. And I think the liquefaction is very interesting right now, and we need to do more research on that kind of type of event. And next, we also did the the pre-exam and post-exam, and by this diagram we can see how the increments of a percentage of the knowledge, we can see the shifting of the range. I think it's also give us a description how the training done successfully. Next, this is the people behind the scene. I want to thank you for Bu Rita, Pak Sadli, Pak Maman, Pak Rahmat, and all the teams from BMKG for your hard work and how you make this event successfully conducted. And for finally, I want to kindly invite our Director General of BMKG to give the closing speech and to declare the closure of our training. Thank you very much.
Thank you, Mrs. Nelly Floridariama, for the report. For the next program, closing speech by Director General of BMKG and officially close the Advanced Earthquake and Tsunami Hazard Training course. To the Honorable Professor Dwi Korita Karnawati, time is yours.
Okay. Well, Bismillahirrahmanirrahim. The honorable trainer, the excellent trainers, there are several trainers which really excellent and helpful to support our capacity development program, especially our colleague the keynote speaker, Dr. Walter De Muni. I think all from USGS. Is that true?
Yes.
Yes, okay. So Dr. Muni and the team, I saw several person in charge to support this training, apart from Dr. Muni. So also the Honorable Deputy Director General for Geophysics, Dr. Muhammad Sadri. Then the Director of the Center for Research and Development, Mrs. Nelly Florida Riama. Thanks for your excellent presentation. I like the pictures, really. It's very good presentation, yeah. And the Director of the Center for Training and Education, Mr. Maman Sudarisman, the Director of Center for Earthquake and Tsunami, Mr. Rahmat Riono, then the Director of the Center for Engineering Seismology, Potential Geophysics and Time Signal, Mr. Bambang Prayitno, and again, Dr. Walter Muni, and the team, also the team of invited speakers. And I like also the speech from Mr. Jambari. Is that correct? I spell Mr. Jambari. Jamhari or Jambari? Jamhari. Okay, from Angkasa Geophysics Station. That's very touching expression. Really great. Yeah, I like that. Of course, to all energized participants of this course and distinguished ladies and gentlemen, good morning, good evening, as well as good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam wabarakatuh.
Well, living in Indonesia somehow like living in danger. If we could not properly manage the risk, we could not properly mitigate the hazards. As we living in very complex and dynamic environment, geological environment, climatology and meteorological environment. I must shift from one laptop to another laptop. At the same time, we also have the coordination meeting to tackle the prevention of disaster due to the rain, because now we are in the transition of dry season into rainy season. And this is the time that we must check all of our preparation. And it was also just talk about West Papua, yeah. But I'm lucky in this laptop, I can be connected to the groups of smart and very energizing people, which really working very hard in the context to mitigate the risk. This is what is the command, the commando, the command in our what we call that the national decree, Indonesian national decree, to protect the people of Indonesia and to protect the country of Indonesia. That the main responsibility of our agency. And I'm very glad that we have very good and productive relations with USGS. And we have about almost 80% of our manpower, or not only men, women power as well. About 80% are the millennials. You can see from this screen how young they are. perhaps including me, but I'm not sure. Late millennial for me, yeah. But I can see it's quite many among them are very young and they are very smart. Just look at or listen to Jamhari's speech. It is very meaningful and make me very optimistic about the future of our agency and the future of Indonesia. If we keep continuing to accelerate the capacity development in all aspects, like in the earthquake, in climate, and in meteorology. As I mentioned before, that our country, our environment is really complex and dynamic, full of uncertainty. For instance, normally, the event of earthquake every year is about 5,000 to 6,000 events with various magnitude. However, starting from the year of 2017, the events increase, becoming more than 7,000 events in 1 year. And suddenly, in the year of 2018, the events jump up into 11,920. And in 2019, just last year, the events of earthquake remain 11,500. So from this evidence, from this data, we realize that somehow the seismic or seismicity activity of the seismicity in Indonesia significantly increase. Meanwhile, the events of extreme weather in the last 30 decades, the trend gradually increased, both the frequency as well as the intensity. This year in January, the intensity of the rainstorm in Jakarta and surrounding area, one day approaching 200 millimeter, just one day. In 2 days, approaching 400 millimeter. And according to our prediction, this intensity continuously increase and the frequency also continuously increase. This makes us realize how important to improve, to accelerate the improvement of our capacity, both in terms of the knowledge, the human resources capacity, as well as the technology. So that's why the support from USGS is really meaningful for us. I learned from the document sent to me, from that document indicating that this training is very comprehensive. It's not only related to the earthquake, but also to the impact of the earthquake, as well as to the volcanism. And even I read also a training related to the climate. That's really meaningful. So again, I really really appreciate, really thankful to all the colleagues of USGS, which really patient, really encouraging to us, to train us, to improve our understanding, as well as our skill and our capacity for all what we need to be more capable to tackle this uncertainty, to tackle this complexity, and to tackle the disaster in more successful way. And I really take serious note on the modern data analysis and also on the statement of Dr. Mooney related to the importance of collection on scientific measurement. We must be able to do that if we really need to make our analysis and prediction really reliable, accurate, and precisely. So I would like to suggest or to remind all of you that this activity must not end by the declaration of closing of this training. This activity must be continued. We still need more training, especially related to the modern data analysis, related to the collection, the better way how to collect the scientific measurement. Even we need to have joint action in the field, perhaps, because now, in order to improve our capacity in early warning, we just installed about, how many? Hang on, let me try to remember. It's about 200 new installment of seismograph. Those including mini frequency or mini seismograph, mini regional seismograph, in order to record or to detect the activity of local fault. So next year we will install 100 more new seismograph. In total, we are preparing to have more than 500 seismograph. After we only have 176 seismograph in the last 10 years. In the last 10 years, we only have 176 seismograph. But within 6 months, immediately, we install almost 200 seismograph. That means we must have collection of better scientific measurement. So that's why I push every young people to continue their research and study in each geophysical station where the new seismograph exists there. So one station must take care of one new active fault. Not the new active fault, but one active fault. So now we have special research by using that data collection on active fault, as well as spatial research on ground motion in Indonesia, ground motion of Indonesia, and also spatial research on tsunami modeling. In this research, we need to work together with other agencies, which we can learn from that agency. So that's why we do expect this training can be continued with the joint research, because we are going to have the new data. And we also need to consult or to discuss about what's next, need to be further improved. What next, the system, the enhanced system or enhanced technology that we must provide it. So please do help us to enhance our knowledge, our capacity in improving our existing system in order to protect the human life, not only the human life in Indonesia, but also in the global community, because the impact of earthquake and tsunami and volcano in Indonesia can spread to other parts of the world. So that's really our obsession, need to be achieved. And I'm really optimistic because I see quite many young people in the screen. So they must very hungry of knowledge, very hungry of new research, very hungry of new technology. I believe they will be able to work harder and harder by listening from the speech of Jamhari. So again, we need to continue this program, and among the young people, there must be a new master, a new doctor. Please also help us to encourage them to continue to study. I believe in United States, there are many excellent universities to where they in which they can learn more from all the excellent experts. Well, that all our dream, and again, great thanks to all of these efforts, great thanks to all the young people also, which learning very with the very strong spirit. And I should apologize if there are still several items or several things need to be further improved. And finally, I would like to formally declare the closing of this training, which means the starting point to move forward another effort for the improvement. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. Thank you very much.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Professor Dwi Korita Karnawati, for the speech and for officially closing Advanced Earthquake and Tsunami Hazard Training course. Ladies and gentlemen, next agenda and the last agenda, we will hold a photo session. To all audiences, I invite you to kindly turn on your camera video. The TSO will take some screenshots. Will handled by Ms. Madonna, please.
Thank you.
Smile.
Yeah, it's pleasure. I take over this photo session. On the count of 3, I will be taking the picture. 1, 2, 3. One, two, three. 1, 2, 3. Yeah, it's done. Thank you very much.
Thank you.
Sorry, one more thing. I have Dr. Sadli. Hello, Dr. Sadli. Yeah, I would like to know, soon we are going to receive the support from World Bank, including to study and some research. Please, then you coordinate with the team. So some of them must go to US to study. The scholarship is available, but we need to discuss further with the team of USGS related to what kind of special research need to further enhance, like a seismic precursor or seismic forecasting or tsunami modeling or whatever, which is very important to us. So please take a special note about the implementation of the scholarship to doctoral and master degree. Thank you very much.
Yes, Bu. Thank you very much. We will coordinate soon with Pak Maman, also with Dr. Muni, and Ibu Nelly, to make coordination about the under IDRI project. We can
under the World Bank project. Okay,
yeah,
great.
thank you very much.
Thank you, everyone.
Thank
Goodbye.
you for
Great, thanks.
Professor
Walter,
Dwi-Korita.
thank you.
Thank you, Prof. Walter, Muni.
Thank you, everyone.
Thank you, Mbak MC. Thank you, Bu Nelly. Everyone,
Mbak
thank you.
Dona,
Great.
thank you. Ibu
Thank you, Mr.
Audia,
Walter
thank you.
Muni.
Ya,
Bu.
Mbak Madonna
thank you
ini
very
juga.
much.
Thank
Ya.
you.
Thank you, Pak Angga dan sebagainya. Thank you. Bye-bye.
Okay, ladies and gentlemen, we come to the end of the closing ceremony for Advanced Earthquake and Tsunami Hazard Training course. On behalf of the organizing committee, I would say thanks to all audiences for your kindly attendance today. Hopefully, we can meet again in another change. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Makasih semuanya.
Sama Ibu.
Mudah-mudahan ada yang lanjut ya, S2, S3.
Amin.
Amin.
Terima kasih semuanya. Terima kasih Bu Nelly.
Makasih Mbak Dona, udah capek dia.
Makasih Bu Kapu, Mbak Dona makasih, Mbak Auzi, semua makasih.
Terima kasih Mbak Roro.
Ya Mbak Roro, spesial
Terima kasih
thanks.
semuanya. Bu Nelly, makasih.
Terima kasih.
Mbak Weni, Mbak Dona, Mbak Audi, Mas Angga. Terima kasih
Sama
banyak.
Mbak.
Ada Bu Puji. Terima kasih banyak teman-teman peserta.
Nanti, oh iya, katanya Walter nanti dia kirim ya, itu referensinya buat teman-teman.
Terima kasih Bu Nelly. Bapak Ibu
Mana
semua.
Jambari, mana dia Mas Jambari apa ini?
Cinle.
Iya Bu.
Keren banget itu speech-nya, mengharu biru loh, mengharu biru itu. Oke, saya pindah ini ya. Makasih semuanya. Kapan-kapan ketemu lagi.
Ya Bu, makasih banyak Bu.
Ya buat inilah acara apa gitu nanti ya. Orangnya sama gitu. Enaknya kalau
Reunian
orangnya
ya.
ya semacam reunian terus
kasih,
apa?
Bu.
Setelah ini apa gitu kan? Gak apa-apa lah.
Ya.
Ada
Tadi-
Zoom itu gampang.
Ya, tadi Bu KB kan juga bilang Bu, kalau bisa ada next collaboration project. Menurut saya sih kalau
Iya.
mau mengekalkan ilmu ya memang salah satunya dengan project.
Iya, siaplah nanti difasilitasi Litbang.
Iya.
Ada Pak Supri kan di sini, masih ada Pak Supri?
Kalau nggak ada Pak Supri, tanya sebelahnya Bu. Bu Puji kan masih ada.
Iya juga. Oke.
Iya, lebih erat Bu sekarang koordinasinya Litbang.
Oh iya.
Alhamdulillah.
Oke, makasih semua ya. Sampai
Iya,
ketemu
Bu.
loh. Saya nggak banyak kenal soalnya nanti kapan-kapan lah. Tapi
Terima kasih
keren.
Bu Nelly.
Keren.
Terima kasih Bapak Ibu.
Terima kasih. Mungkin bisa dikondisikan Bu Don.
Oh
Ya.
iya.
Ketemuan.
Oh ya, dikondisikan untuk pertemuan selanjutnya ya.
Oh iya, karena kan kita belum pernah sebenarnya ngobrol. Setelah ini apa? Kemarin kan ada mereka gitu ya. Terus ini kalau yang tugasnya belum selesai berarti nggak lulus kan ya?
Nggak dikasih sertifikat Bu. Sertifikatnya
Ya,
ditahan
makanya
biasanya.
Itu makanya dibenerin dulu supaya ini. Karena saya udah lihat itu hampir setengahnya nggak dapat sertifikat loh. Kasihan juga kan?
Iya, tapi kayaknya teman-teman ini adalah alumni dari Diklat, PSHA, dan PET sebelumnya. Jadi pasti udah paham banget deh bahwa sertifikat itu ditahan sebelum
gitu ya?
diuber-uber fasil. Iya. Dan
Saya
teman-teman
baru
yang
tahu. Saya tadi lihatnya, aduh gimana ya gitu. Ya udah
Iya,
dikerjain aja yang belum.
sampai
Nanti
kapan
kita-
batasnya Mbak Don?
Nah itu harus ada tuh.
Senin lah, Senin nggak apa-apa. Mungkinnya Bu Nelly ya.
Senin.
Oh ya
Ya.
Senin. Oh saya pikir masih lama enggak ya Senin ya. Wow. Oke.
Tergantung
Kalau
tugasnya
lama
sih.
terlupakan.
Nanti yang puslitbang awas aja kalau belum Senin. Oke, makasih ya. Sampai ketemu nanti lah Mbak Dona, nanti ada waktu ya.
Iya,
Kita
iya,
ini.
Bu. Makasih, Bu, ya.
Makasih. Nanti saya harus ngobrol sama Walter juga selanjutnya.
Siap, Bu. Terima kasih. Mbak Don, mungkin YouTube-nya bisa dinonaktifkan
Oh
dulu.
iya. Oke.
Kalau ini sudah selesai, mungkin kita persilakan untuk teman-teman. Mungkin ada yang mau zuhur, ada yang mau Jumatan.
Iya loh, udah persiapan.